Welcome to Ancient Relics Keeper, where forgotten civilizations, unexplained wonders, and ancient secrets come back to life. Ready to unravel the mystery? Let's begin the journey. Beneath the frozen ice sheets of Antarctica and the Arctic lie secrets of a lost world, a world without ice. Fossils of lush green forests, tropical plants, and giant reptiles have been found in the coldest places on Earth. These discoveries reveal a deep past when our planet was dramatically different and much, much warmer. When we picture our planet from space, we see a familiar and beautiful blue marble, capped at both ends by brilliant white shields of ice. The polar regions, the Arctic and the Antarctic, are our planet's great frozen wildernesses, landscapes defined by ice, snow, and extreme cold. Antarctica, in particular, is the coldest, driest, and highest continent on Earth, a vast and desolate desert of ice, in some places over 2 miles thick. It is a land so hostile to life that for most of human history, it was a complete mystery, a blank space on the map labeled Terra Australis Incognita, the unknown southern land. Today we have mapped its surface and plumbed the depths of its ice, but the image remains the same. A world of white. But what if this image, the one we consider so permanent and fundamental to our planet's identity, is just a temporary phase? What if the true history of Antarctica is not white but green? This is the story of the discoveries that have shattered our perception of the polar world. A story of fossils found beneath the ice that tell of a time when the South Pole was not a frozen wasteland, but a lush, vibrant, and living continent. Our journey begins with a single humble fossil leaf, a clue that would ultimately help to prove one of the most revolutionary scientific theories of all time. The story of Antarctica's green past begins long before we could drill through its ice sheets or even set foot on its shores. It begins in the early 20th century, with the heroic age of Antarctic exploration. Men like Robert Falcon Scott and Ernest Shackleton were leading grueling expeditions into the continent's interior, not just for the glory of reaching the South Pole, but also for science. On Scott's ill-fated Terra Nova expedition in 1912, as his team was making their desperate and ultimately fatal return journey from the pole, they made a detour to collect geological samples from the Transantarctic Mountains. Even in their weakened and starving state, they knew the scientific importance of what they were doing. They hauled over 35 pounds of rock samples with them on their sledges, a burden that may have contributed to their demise. When their frozen bodies were discovered months later, the precious rock samples were found alongside them. And within those rocks was something extraordinary. They were not just rocks, they were coal seams. And within that coal were the clear, fossilized impressions of plant leaves. These were the leaves of a plant called Glossopteris. This was a type of extinct seed fern, a woody tree-like plant that formed vast forests during the Permian period, around 250 million years ago. The discovery was a profound puzzle. Coal is formed from the compressed remains of vast amounts of plant matter. To find coal seams in Antarctica meant that the continent must have once been covered in dense forests. And Glossopteris was known to be a temperate plant, not a polar one. How could a temperate forest have grown in a place that is now the coldest on Earth? At the time, most scientists believed in the permanent continent theory, the idea that the continents had always been fixed in their current positions. To explain these polar forests, they came up with complex theories about ancient land bridges that had since sunk beneath the waves, or dramatic shifts in the Earth's axis. But a German meteorologist named Alfred Wegener had a much more radical idea. He proposed the theory of continental drift, suggesting that the continents were not fixed, but had moved over geological time. He argued that all the continents had once been joined together in a single supercontinent, which he called Pangaea. The discovery of Glossopteris fossils in Antarctica became one of Wegener's key pieces of evidence. Fossils of this exact same plant had also been found in South America, Africa, India, and Australia. How could the same temperate plant be found on continents now separated by thousands of miles of ocean? For Wegener, the answer was simple. They weren't separated at the time. All these landmasses were once connected, clustered together in the southern part of Pangaea. Antarctica was not always at the South Pole. It was once part of a much larger, warmer landmass, and it had slowly drifted to its current frozen position. Wegener's theory was ridiculed by the scientific establishment for decades. He was a meteorologist, not a geologist, and he couldn't propose a convincing mechanism for how the continents could possibly move. But the evidence from the fossils was undeniable. The silent stone leaves of Glossopteris, recovered by Scott's doomed expedition, were a message from the past, a clue that would eventually be proven correct. By the 1960s, with the discovery of seafloor spreading and the development of the theory of plate tectonics, Wegener was vindicated. The continents had indeed moved, and Antarctica had once been green. The Glossopteris fossils were the first crack in the ice, the first hint of a dramatically different polar past. But the discoveries that were to come would be even more shocking, revealing a world that was not just temperate, but practically subtropical. For many years, our knowledge of Antarctica's ancient flora was limited to these older, Permian-era fossils. But what was the continent like during a more recent, and globally much warmer period, the age of the dinosaurs? The Cretaceous period, from roughly 145 to 66 million years ago, was one of the warmest periods in Earth's history. It was a classic greenhouse world, with high levels of atmospheric carbon dioxide, and no permanent ice caps at either pole. During this time, Antarctica was still located over the South Pole, but the global climate was so warm that its polar position didn't mean it was frozen. Scientists had long suspected that the continent must have been vegetated during this time, but finding direct evidence was incredibly difficult. The ancient soils and delicate plant remains were buried deep beneath the massive West Antarctic ice sheet. But in 2017, a team of international scientists aboard the German research vessel Polarstern set out to change that. They traveled to the Amundsen Sea, off the coast of West Antarctica, an area where the ice sheet extends out over the ocean. Their mission was to drill into the seabed, through layers of modern sediment, to try and recover a core sample of the bedrock from the Cretaceous period. They used a specialized seafloor drilling rig, lowering it through hundreds of meters of frigid water. The drill bit churned through the loose, recent sediments on the ocean floor, and then hit something harder: the ancient layers from 90 million years ago. They carefully drilled a core and brought it back up to the ship. When they split the core open in the ship's laboratory, they were met with a sight that no human had ever seen before. It was not gray marine clay or hard bedrock. The core was a strange color, a dark brownish gray, and it was filled with a fine, dense network of filaments. The scientists were looking at a perfectly preserved slice of ancient soil. It was the fossilized floor of a 90-million-year-old forest. The fine filaments were the fossilized root systems of the trees and plants that had grown there. The soil was rich in organic matter, the decayed remains of ancient leaves and wood. The preservation was so exquisite that it was like looking at a core sample from a modern forest floor. The team took the core back to their labs for detailed analysis. Using X-ray CT scanners, they were able to create a 3D digital model of the root networks, seeing how they intertwined and grew through the ancient soil. But the most incredible discovery came when they analyzed the soil under the microscope. It was packed, absolutely teeming with fossilized pollen and spores. They identified the pollen of ancient conifers, relatives of modern fir and cedar trees. They found the spores of a huge diversity of ferns and mosses that would have formed a lush undergrowth. The types of plants they identified were not hardy, cold-adapted species. They were the kind of plants you would find in a temperate rainforest, like the forests of modern-day New Zealand or the Pacific Northwest of North America. Based on this incredible floral evidence, the scientists were able to reconstruct the ancient environment with stunning accuracy. 90 million years ago, the coast of West Antarctica was a swampy, temperate rainforest. The average annual temperature was around 12 degrees Celsius, about 54 degrees Fahrenheit, with summer temperatures likely reaching up to 19 degrees Celsius, 66 Fahrenheit. The rainfall was high, comparable to that of modern-day Wales. This was a world away from the frozen desert of today. It was a green, wet, and vibrant world. The discovery was a bombshell. It was the first direct, physical proof of what Antarctica's climate and environment were actually like during this peak greenhouse period. It was a snapshot of a lost ecosystem, a forest at the bottom of the world. And as other discoveries would soon show, this forest was not empty. A forest, no matter how lush, is just a landscape. What brings it to life are the animals that inhabit it. For years, the idea of large animals living in Antarctica, even a green Antarctica, was considered unlikely. How could they survive the long, dark polar winter, which would have lasted for several months? But just as the fossil plants began to rewrite the story of the continent's climate, fossil animal bones began to rewrite the story of its fauna. The hunt for Antarctic dinosaurs began in earnest in the 1980s and 90s, focused on the one part of the continent where ancient rocks are exposed and not covered by ice, the Antarctic Peninsula. This long finger of land reaches north towards South America and has a relatively milder climate today, meaning that snow and ice melt during the summer, revealing the fossil-bearing rocks beneath. It was here, on islands like James Ross Island and Vega Island, that paleontologists began to find the undeniable proof that dinosaurs had once called Antarctica home. They found the fossilized bones of plesiosaurs and mosasaurs, giant marine reptiles that swam in the cool polar seas that surrounded the continent. But the most exciting finds were the land dwellers. They unearthed the remains of ankylosaurs, the heavily armored, tank-like herbivores, famous for their defensive body plates and their powerful tail clubs. Finding these animals here proved that there was enough low-growing vegetation, like ferns, for them to eat. They found the remains of hypsilophodonts, small, agile, two-legged herbivores that would have browsed on the forest undergrowth. And then came the giants. Paleontologists discovered the fossilized vertebrae and limb bones of titanosaurs. The titanosaurs were a group of sauropod dinosaurs, the long-necked, long-tailed giants that were the largest land animals ever to walk the earth. Finding a titanosaur in Antarctica was a profound discovery. These were enormous animals, some reaching lengths of over 50 feet. An animal that large would have needed to consume a huge amount of plant matter every single day. Its presence is a powerful testament to just how rich and productive the Antarctic forests must have been. They weren't sparse, struggling woodlands. They were lush, dense forests capable of supporting a population of these giant herbivores. The dinosaur discoveries proved that the Antarctic rainforest was not a silent place. It was a living, breathing ecosystem, filled with the sounds of giant animals crashing through the undergrowth. And where there are herbivores, there must also be predators. The fossil record for Antarctic predators is still scarce, but paleontologists have found the teeth of theropod dinosaurs, the group of two-legged carnivores that includes famous killers like Tyrannosaurus rex. A complete skeleton has yet to be found, but the teeth are proof that hunters stalked these polar forests, preying on the giant herbivores. The animal fossils completely changed our picture of the continent. They populated the green world that the plant fossils had revealed. And they answered the critical question of the polar winter. How did these dinosaurs survive for months of total darkness and cold, albeit not freezing temperatures? The answer is that they were likely adapted in ways we are only just beginning to understand. Some of the herbivores may have been able to enter a state of prolonged dormancy, a kind of hibernation, to conserve energy during the dark months. Or, more likely, they were adapted to browse on the types of vegetation, like conifers and ferns, that would have remained available throughout the winter. And many dinosaurs, unlike modern reptiles, are now thought to have been at least partially warm-blooded, which would have allowed them to remain active in the cool, dark conditions. The forest's inhabitants were a unique community of animals, perfectly adapted to a unique environment. A world of polar light and polar darkness, a world without ice. When we take all of this evidence and put it together, the Glossopteris leaves from the Permian, the 90-million-year-old rainforest floor from the Cretaceous, and the fossilized bones of the dinosaurs that roamed that forest, an undeniable and breathtaking picture emerges. For vast stretches of geological time, Antarctica was not a world of white. It was a world of green. It was a continent covered in lush, temperate, and even subtropical vegetation. It was a world teeming with life, from the smallest insects to the most colossal dinosaurs. It was a world completely, utterly, and fundamentally different from the one we know today. And the most critical piece of this entire puzzle is the fact that during these warm periods, Antarctica was still located in its polar position. This wasn't a case of the continent being in the tropics. It was a polar continent, experiencing the same extreme light cycles of 24-hour summer sun and months of winter darkness that it does today. The only difference was the climate. The global thermostat was turned up so high that even at the South Pole the temperatures rarely, if ever, dropped below freezing. This fact leads to the most important conclusion of all. There was a time when our planet had no permanent ice at the poles. The presence of these Antarctic forests is the ultimate proof of a greenhouse Earth, a state that our planet has been in for much of more of its history than the icehouse state we currently inhabit. The fossils from Antarctica are more than just scientific curiosities. They are a fundamental challenge to our perception of our own planet. They show us that the world we consider normal is anything but. They are a message from a warmer past, a past when the idea of a permanent, continent-sized ice sheet at the South Pole would have been as alien a concept as a forest is to us there today. They are the keys to understanding the incredible capacity of our planet to change, and a powerful glimpse into a lost green world at the very bottom of the Earth. The fossil discoveries from Antarctica paint a stunning picture of a lost green world at the South Pole, a world of temperate rainforests and giant dinosaurs. This evidence single-handedly proves that our planet has experienced periods of extreme warmth in its deep past, times when the polar regions were completely free of ice. But was this phenomenon confined to the southern hemisphere? To find the answer, we must now travel to the other end of the world, to the high Arctic. Here, in a land of sea ice, polar bears, and the shimmering aurora borealis, an equally shocking and even more paradoxical collection of fossils has been unearthed. The discoveries from the Arctic tell the same story as those from Antarctica, but with a different cast of characters, creatures so bizarrely out of place in their modern environment that they force us to confront the sheer scale of global climate change. This is the story of the Arctic paradox, a time when cold-blooded reptiles and subtropical mammals thrived in the land of the midnight sun. Our journey takes us to one of the most northern and desolate landmasses on Earth. Our focus now shifts to the Canadian Arctic archipelago, a vast collection of islands scattered across the Polar Sea. Specifically, we traveled to Ellesmere Island. Located at a latitude of over 78 degrees north, Ellesmere Island is a place of profound and stark beauty. It is a land of towering ice-capped mountains, vast glaciers, and barren rocky plains. For most of the year, it is locked in ice and snow, with temperatures that can plummet to -40 degrees Celsius. It is one of the last truly wild places on Earth, a place where the modern world seems a distant memory. And yet, scattered across this frozen landscape are patches of exposed rock sedimentary basins that have, against all odds, preserved a perfect snapshot of a time when this island was not a frozen desert, but a warm, wet, and vibrant ecosystem. These fossil-bearing formations, particularly the Eureka Sound Group, date back to the Eocene epoch, a period of geological time that lasted from about 56 to 34 million years ago. The Eocene was the warmest period of the last 66 million years, a time of peak greenhouse conditions, and the fossils found on Ellesmere Island provide our most detailed and spectacular window into what the Arctic was like during this global heat wave. For decades, paleontologists have been making arduous expeditions to this remote and challenging location. The field season is short and the logistics are a nightmare, but the rewards have been extraordinary. The rocks of Ellesmere Island have yielded an incredible trove of exquisitely preserved fossils. They have found the fossilized leaves, seeds, and even entire mummified logs of ancient trees. The flora was not the sparse, low-lying tundra we see today. It was a dense forest of large trees, including Dawn redwoods, a relative of the giant sequoias of California, as well as birch, sycamore, and fir. These were not stunted, wind-blown shrubs. These were forests of tall, majestic trees, indicating a mild and wet climate. This in itself was a remarkable discovery, but it was the animal fossils found amongst the petrified forests that would truly shatter all expectations. The evidence they found proved, beyond any doubt, that this high Arctic island was once home to a community of animals that today we would associate with the warm, humid swamps of the American South. The single most stunning and paradoxical discovery to come from the Eocene sediments of Ellesmere Island was the fossilized remains of alligators. Paleontologists have unearthed numerous bones, including vertebrae and distinctive scutesque bony plates from their skin armor, that are undeniably from a member of the alligator family. This discovery is a profound climatic puzzle. Alligators, like all modern crocodilians, are cold-blooded or ectothermic. This means they cannot generate their own body heat and are completely dependent on the temperature of their external environment to regulate their metabolism. They are creatures of warmth. The American alligator today is found in the southeastern United States, in places like Florida, Louisiana, and Georgia. They can tolerate a brief, mild frost, but they absolutely cannot survive a prolonged, hard freeze. A single, harsh winter would be a death sentence for an entire population. To find the remains of their ancient relatives living on an island that is now well inside the Arctic Circle is, to put it mildly, a shock. This was not a case of a single lost alligator that somehow strayed thousands of miles to the north. The number of fossils found indicates that there was a healthy breeding population that lived on Ellesmere Island for thousands, if not millions, of years. For this to have been possible, the climate of the Eocene Arctic must have been radically different from today. The presence of alligators provides a very specific and non-negotiable set of climatic parameters. It tells us that the average annual temperature must have been significantly warmer than it is today. But more importantly, it tells us something crucial about the winters. The coldest month of the year could not have dropped below freezing for any extended period. The lakes and swamps in which these alligators lived could not have frozen solid. The Eocene Arctic, even during the long dark polar winter, must have remained a mild, frost-free environment. This is a staggering thought. It fundamentally contradicts our entire modern experience of what the Arctic is. The alligator fossils are a biological thermometer, a direct reading of the ancient climate that tells us this was a warm, temperate, and almost subtropical world. The image of alligators basking on the banks of a swampy river, surrounded by a redwood forest, under the pale light of a low Arctic sun, is one of the most powerful and mind-bending pictures that the fossil record has ever given us. It is a direct glimpse into a different version of our planet. And the alligators were not the only warm-blooded refugees found in this polar paradise. As paleontologists continued to explore the fossil beds of Ellesmere Island, the menagerie of out-of-place animals grew even stranger. Alongside the alligators, they found the fossilized shell fragments and bones of giant tortoises. Like alligators, tortoises are cold-blooded reptiles that are restricted to the warmer parts of the world today. The giant tortoises we know, like those from the Galapagos Islands or Aldabra Atoll, are icons of tropical and subtropical environments. Finding their ancient relatives lumbering through the forests of the high Arctic adds another layer of impossibility to the scene. A large tortoise is a slow-moving creature with a slow metabolism. It would have had no way of surviving a frozen winter. Its presence confirms, once again, the mild, frost-free nature of the Eocene Arctic climate. It also tells us about the richness of the vegetation. A giant tortoise is a voracious herbivore. For a population of them to survive, there must have been an abundant and year-round supply of low-growing plants, ferns, and other greenery for them to eat. But perhaps the most geographically bewildering discovery of all was the fossilized jawbones and teeth of an animal known as a colugo, or a flying lemur. Modern colugo are not true lemurs, but are a unique order of gliding mammals. They have a thin membrane of skin that stretches between their limbs, allowing them to glide for long distances from tree to tree. Today, the world's 2 living species of colugo are found exclusively in the tropical rainforests of Southeast Asia. They are the ultimate specialists of the tropical canopy. To find their ancient ancestor on Ellesmere Island is a zoological bombshell. It is the fossil equivalent of finding a polar bear in the Amazon rainforest. It's not just that the climate is wrong, the entire geography is wrong. The discovery completely rewrites the story of this animal's evolutionary history and its dispersal across the globe. It suggests that during the warm Eocene, these animals had a much wider, almost global distribution, and that the modern Southeast Asian populations are just the last surviving remnants of a once great dynasty. The presence of the flying lemur also tells us something crucial about the structure of the forest itself. These are animals that need a dense, continuous forest canopy to move around. Their presence confirms that the Eocene Arctic was not just a collection of scattered groves, but a true dense forest, with tall trees growing close enough together to allow these remarkable creatures to glide from one to the next. The list of strange, warm-weather animals goes on. Scientists have also found the remains of hippo-like and rhino-like mammals, large herbivores that further attest to the productivity of this lost ecosystem. Each new discovery adds another brushstroke to the painting, confirming the same incredible story. The Arctic of 50 million years ago was not a polar desert. It was a thriving, vibrant, and surprisingly diverse world, teeming with animals that we would today consider to be exiles from the tropics. When we assemble all the evidence from Ellesmere Island, the fossilized redwood forests, the bones of the alligators, the shells of the giant tortoises, and the jaws of the flying lemurs, a clear and detailed picture of this lost Arctic world comes into focus. This was not a cold or even a temperate environment. This was a warm, humid subtropical world. The landscape would have been dominated by vast, swampy lowlands, filled with slow-moving rivers, lakes, and wetlands. These wetlands would have been choked with aquatic vegetation, the perfect habitat for a thriving population of alligators. On the slightly higher, better-drained ground, dense forests of towering dawn redwoods, firs, and other conifers would have grown, their canopy providing a home for gliding mammals and a diverse array of other creatures. The climate would have been mild and rainy year-round. The summers, with 24 hours of sunlight, would have been incredibly productive, leading to explosive plant growth. And crucially, the winters, despite the months of polar darkness, would have remained mild and frost-free. The average temperature would have been more like that of modern-day North Carolina or northern Florida than that of the modern Arctic. This ancient ecosystem is a paradox. It is a world that, according to our modern experience, simply should not exist. A warm subtropical swamp at 78 degrees north latitude seems like a contradiction in terms. How could such a world be possible? How could the Arctic, even during a global greenhouse period, stay warm enough to support alligators and tortoises, especially during the long sunless winter? It defies our common-sense understanding of how the planet works. It shows us that our modern perspective is incredibly limited. We are living in a geological instant, a cold icehouse phase, and we mistakenly assume that this is the planet's normal state. The fossils from Ellesmere Island are a powerful corrective to this view. They prove that a very different set of climatic rules can, and did, apply to our planet. They force us to ask the most fundamental questions about the Earth's climate system. What were the forces that could create and sustain such a warm polar world? The answer lies not in the Arctic itself, but in the global systems that control our planet's temperature. The arrangement of the continents, the chemistry of the oceans, and most importantly, the composition of the atmosphere itself. The alligators of the Arctic are not just a curiosity. They are a key piece of evidence in the larger mystery of Earth's great climate shifts, a mystery that has profound implications for our own future. The evidence from the ends of the Earth is undeniable. The fossils of lush rainforests and dinosaurs in Antarctica, and the remains of alligators and giant tortoises in the high Arctic, all tell the same, seemingly impossible story. Our planet has experienced long periods of extreme warmth in its past, times when the polar regions were completely free of ice and teeming with life. This is not a theory. It is a fact written in the stone and soil of the planet itself. But this fact presents us with a profound and fundamental puzzle. How is this possible? What forces could be powerful enough to transform the entire planet into a greenhouse world, to keep the poles so warm that cold-blooded reptiles could thrive there, even through the long dark polar winters? To answer this, we must now move from the what to the how. We must investigate the science behind this ancient superwarmth, exploring the great geological and atmospheric mechanisms that control our planet's thermostat. This is a journey into the deep-time climate science of our world, a story that begins with the very shape of the planet itself. The first question we must ask is whether this ancient warmth can be explained simply by the fact that the continents were in different positions. We know from the theory of plate tectonics that the Earth's continents are not static. They are constantly in motion, drifting across the surface of the planet over millions of years, joining together to form supercontinents and then breaking apart again. Could the warmth of the poles simply be a result of them not being at the poles at all? In the case of the Permian forests of Antarctica, this is certainly a large part of the explanation. During the Permian period around 250 million years ago, Antarctica was not an isolated continent at the South Pole. It was a central piece of the great southern supercontinent Gondwana, which was itself part of the even larger supercontinent Pangaea. It was located in a more temperate, mid-latitude position, much like Australia or New Zealand today. Its warmer climate during this time is therefore not so surprising. But this explanation does not work for the later warm periods. By the time of the Cretaceous period 90 million years ago, when rainforests flourished in West Antarctica, the supercontinent of Pangaea had broken up, and Antarctica had already drifted very close to its current position over the South Pole. And by the Eocene epoch 50 million years ago, when alligators swam in the Arctic, the continents were arranged in a configuration that was very similar to the one we see today. North America and Eurasia were clustered around the Arctic Ocean, and Antarctica was firmly anchored over the South Pole. So while the changing positions of the continents and the associated shifts in ocean currents certainly played a role in regional climates, they cannot, by themselves, explain the extreme warmth of the poles during these later periods. We can't solve the puzzle simply by rearranging the map. There must have been another, more powerful and more global force at play, a force that was capable of warming the entire planet, from the equator to the poles. The answer to what that force was lies not in the ground beneath our feet, but in the air all around us. The primary driver, the great thermostat that has controlled Earth's climate for billions of years, is the composition of our atmosphere, specifically the concentration of greenhouse gases. The greenhouse effect is a natural and essential process. Gases like water vapor, carbon dioxide, CO2, and methane act like a transparent blanket around our planet. They allow the sun's short-wave radiation, sunlight, to pass through and warm the Earth's surface, but they trap some of the outgoing long-wave radiation heat that the Earth radiates back into space. Without this natural greenhouse effect, the average temperature of our planet would be about -18 degrees Celsius, and the entire Earth would be a frozen ball of ice. But the thickness of this blanket can change. When the concentration of greenhouse gases in the atmosphere is low, more heat escapes into space, and the planet cools down, leading to an icehouse world like the one we are in today, with ice caps at the poles. When the concentration of greenhouse gases is high, less heat escapes, and the planet warms up dramatically, leading to a greenhouse world, with no permanent ice anywhere. The science is now overwhelming that the great warm periods of the past, like the Cretaceous and the Eocene, were caused by one primary factor. The atmosphere contained vastly higher concentrations of carbon dioxide than it does today. But how do we know this? We can't directly measure the air from 50 million years ago. Scientists have developed a number of clever proxies, or indirect methods, to reconstruct the atmospheric CO2 levels of the deep past. One method is to study the tiny, fossilized pores or stomata on the surface of ancient plant leaves. Plants breathe in CO2 through these pores. When CO2 levels in the atmosphere are high, plants don't need to be as efficient at capturing it, so they grow leaves with fewer stomata. When CO2 levels are low, they grow leaves with a higher density of stomata to maximize their intake. By counting the number of stomata on fossilized leaves and comparing them to their modern relatives, scientists can get a surprisingly accurate estimate of ancient CO2 levels. Another method is to study the chemical composition of fossilized soil minerals, or the shells of tiny marine organisms. The specific isotopes of elements like boron and carbon that they incorporate into their structures are directly influenced by the amount of CO2 in the atmosphere and oceans. By using these and other proxies, scientists have been able to reconstruct the history of atmospheric CO2 with remarkable detail. And the results are unambiguous. During the warmest parts of the Cretaceous and the Eocene, atmospheric CO2 levels were not just a little bit higher than today, they were many times higher. Pre-industrial CO2 levels were around 280 parts per million, ppm. Today, due to human activity, they have risen to over 420 ppm. But during the Eocene, CO2 levels are estimated to have been over 1,000 ppm, and perhaps as high as 2,000 ppm during parts of the Cretaceous. This was the missing ingredient. The Earth's atmosphere had a much thicker greenhouse blanket. This incredible concentration of CO2 was the engine that drove the planet's thermostat to its highest settings, creating a world so warm that even the poles could not freeze. The source of this ancient CO2 was entirely natural, released slowly over millions of years by intense and prolonged volcanic activity, which spewed massive quantities of the gas into the atmosphere. This high level of CO2 is the ultimate cause of the polar warmth, but it still leaves one tricky question to be answered. Even with the supercharged greenhouse effect, the poles still face a fundamental energy problem: the polar winter. For several months each year, the polar regions are tilted away from the sun, receiving little to no direct sunlight. This is the polar night. In our modern world, this lack of solar energy allows the poles to get incredibly cold, even with our current greenhouse effect. So, how did the Eocene Arctic stay warm enough for alligators to survive through a winter that was completely dark for 3 or 4 months? How did the Antarctic rainforests survive a similar period of darkness? This is one of the most challenging puzzles of paleoclimatology, and the answer seems to lie in a powerful combination of a thick greenhouse blanket and a very efficient global heat distribution system. The first part of the solution is the sheer power of the greenhouse effect at those high CO2 concentrations. The blanket was so thick that it was incredibly efficient at trapping the heat that had been absorbed by the planet during the sunlit months. While the poles would have cooled down during the winter, they would have been starting from a much higher baseline temperature, and the thick atmosphere would have slowed the rate of heat loss dramatically. The winters would have been dark and cool but not freezing. Think of it like a well-insulated house. Even if you turn off the furnace, it will stay warm for a long time. The greenhouse Earth was a very well-insulated planet. But insulation alone was probably not enough. The second, and equally crucial, part of the solution was the way heat was transported around the planet by the oceans. The ocean acts as a massive, global conveyor belt, absorbing heat in the tropics and transporting it towards the poles. The specific configuration of the continents and the absence of large ice sheets during these warm periods allowed for a very different and much more efficient pattern of ocean circulation. Warm ocean currents, originating in the tropics, were able to penetrate much further into the polar regions than they can today. In the north, the warmer, less restricted Atlantic Ocean could have pumped huge amounts of heat into the Arctic basin. In the south, the ocean currents flowing around Antarctica would have been much warmer, keeping the continental margins from freezing. These warm currents acted like a giant, global heating system, constantly replenishing the heat that was being lost to space during the polar winter. The combination of these two factors, a thick greenhouse blanket that prevented heat from escaping, and a powerful ocean circulation system that constantly imported new heat from the tropics, is the key to solving the polar winter paradox. It was this synergy that allowed the poles to remain mild and frost-free year-round, creating a stable, habitable environment for the incredible ecosystems we see in the fossil record. The science behind the superwarmth shows us that it was not magic. It was the result of a specific set of physical and chemical conditions on our planet. And this leads us to the most pressing and relevant question of all. We have seen that the great warm periods of the past were driven by high levels of atmospheric carbon dioxide. This naturally leads to a critical and somewhat frightening question. Could it happen again? And if so, what would it look like? The ancient greenhouse worlds of the Eocene and the Cretaceous are not just geological curiosities. They are natural experiments, real-world case studies of what happens to our planet when the global thermostat is turned up to its highest settings. They provide us with our best, and perhaps our only guide to understanding the potential consequences of our own modern-day experiment with the atmosphere. Today, humans are releasing massive quantities of carbon dioxide into the atmosphere by burning fossil fuels, a process that is happening at a rate far faster than even the most intense periods of ancient volcanism. We are, in effect, recreating the atmospheric conditions of the deep past, but on a geological timescale that is almost instantaneous. By studying these ancient warm periods, scientists can test and refine their climate models, using the past to predict the future. The fossil record from the poles provides a stark and unambiguous warning. It shows us that there is a direct and powerful link between atmospheric CO2 and polar temperatures. When CO2 levels were high, the ice sheets were non-existent. This tells us that our current polar ice caps are not a permanent feature of the planet. They are highly sensitive to the global climate, and they can and have disappeared in the past when conditions were right. The most direct and catastrophic consequence of this would be a dramatic rise in global sea levels. If the Greenland and West Antarctic ice sheets were to melt completely, a process that would be locked in by a return to Eocene-level CO2 concentrations, global sea levels would rise by tens of meters. This would inundate coastal cities around the world, displacing hundreds of millions of people and redrawing the map of our continents. The polar fossils are a geological warning sign for places like Miami, Shanghai, and Amsterdam. Furthermore, the ancient ecosystems show us how life responds to a warmer world. While the polar regions might become lush and green, other parts of the world would likely become uninhabitable. The tropics could become so hot that they would be lethal for many plants and animals, including humans. Weather patterns would shift dramatically, leading to more extreme storms, droughts, and floods. The past shows us that the Earth system is capable of far more dramatic and rapid shifts than we once thought possible. We are currently pushing the system towards one of these ancient tipping points. The alligators in the Arctic and the forests in Antarctica are not just relics of a distant past. They are a preview of a potential future. They are a message, written in stone and delivered to us from 50 million years ago. A message that warns us of the profound and irreversible consequences of altering the delicate chemical balance of our planet's atmosphere. The science behind the superwarmth is not just an academic exercise. It is the most important story for the future of our own civilization. We have journeyed to the frozen ends of the Earth and found the ghosts of a green and vibrant past. We have seen the evidence for temperate rainforests at the South Pole and subtropical swamps teeming with alligators at the North Pole. And we have explored the powerful science behind this ancient warmth, a science driven by high levels of atmospheric carbon dioxide and a fundamentally different global climate system. These discoveries are more than just fascinating scientific curiosities. They are profound and paradigm-shifting. They force us to reconsider our most basic assumptions about our planet, its history, and its future. The fossils under the ice are not just dead things. They are messengers from a lost world, and the message they carry has deep and far-reaching implications for us today. We must now explore what these discoveries truly mean, how they rewrite our planet's history, what they teach us about the limits of life, and what they warn us about the path we are currently on. The first and most fundamental implication is that our entire modern vision of planet Earth is skewed. For all of human history, we have lived in a world with ice at its poles. The image of the white polar caps is deeply ingrained in our collective consciousness. We see it in every atlas, on every globe, in every satellite photograph. We think of this icehouse state as normal, as the default condition of our planet. The great ice sheets of Antarctica and Greenland feel permanent, eternal, a fixed feature of the world. But the fossils under the ice tell us a radically different story. They prove that our current geological moment is, in the grand scheme of things, the exception, not the rule. The discoveries of polar forests and warm-weather animals show that for vast stretches of its history, our planet had little to no permanent ice at all. For most of the last 250 million years, the entire age of the dinosaurs and the age of mammals that followed the Earth was a greenhouse world. The icehouse conditions we live in today, which began to set in only around 34 million years ago, when the Antarctic ice sheet first began to form, represent a relatively short and unusual cold snap in the planet's long warm history. This completely rewrites our planet's biography. It's like discovering that a person you've only ever known as a quiet, reserved adult was actually a loud, flamboyant rock star for most of their life. The personality you thought was normal is just a recent phase. The Earth's true long-term personality is not one of icy poles, but of global pole-to-pole warmth. This is a profound shift in perspective. It means that the great polar ice sheets, which we see as such powerful and permanent features, are in fact geologically fragile and ephemeral. They have disappeared in the past, and the evidence shows that they can disappear again if the right climatic conditions are met. This discovery forces us to see our planet not as a static backdrop for life, but as a dynamic and incredibly variable system, capable of shifting between radically different climatic states. The world we have built our civilization in, the stable Holocene climate of the last 10,000 years, is a precious and perhaps temporary gift. The fossils from the poles are a humbling reminder that we are living on a planet with a deep and wild past, a past that holds the potential for futures we can barely imagine. This new understanding of our planet's history also forces us to reconsider the very limits of life itself. The discovery of complex ecosystems thriving at the poles during these ancient warm periods is a powerful lesson in the resilience and adaptability of life. It pushes the known boundaries of what is possible for terrestrial and aquatic organisms. For decades, it was assumed that even if the poles were warmer, they would have been inhospitable to complex life because of one unchangeable factor: the polar light cycle. The regions above the Arctic and below the Antarctic circles experience months of 24-hour daylight in the summer and months of continuous darkness in the winter. How could a complex forest ecosystem, which depends on sunlight for photosynthesis, survive a winter that was 3 or 4 months long and completely dark? How could large active animals find enough food to survive this long dark period? The fossils provide the answer. Life found a way. The plants that made up these polar forests were a unique mix of evergreen and deciduous species. The conifers, like the ancient relatives of firs and pines, would have retained their needles, ready to begin photosynthesizing the moment the sun returned in the spring. The deciduous trees, like the dawn redwoods, would have dropped their leaves and entered a state of dormancy during the dark winter, just as trees in temperate regions do today during the cold winter. They were adapted to a rhythm of darkness and light, rather than a rhythm of cold and warmth. The forest floor would have been a thick mat of ferns, mosses, and fungi, many of which are well adapted to low light conditions. The animals, too, must have had remarkable adaptations. The large herbivores, like the Antarctic titanosaurs, may have had slower metabolisms that allowed them to survive on the lower-quality evergreen foliage available during the winter. Some smaller animals may have hibernated or entered a state of torpor. The alligators and tortoises of the Arctic, being cold-blooded, would have become very sluggish during the cool, dark winter, dramatically reducing their energy needs until the sun and warmth returned. What this shows us is that the polar night in itself is not a barrier to complex life. As long as the temperatures remain above freezing, life's incredible evolutionary engine is capable of producing unique solutions to unique environmental challenges. It demonstrates that the limiting factor for life at the poles is not the lack of light, but the presence of ice. Remove the ice and life can, and will flourish in the most extraordinary ways. This has profound implications for our search for life elsewhere in the universe. We often think of habitable planets as needing a perfect Earth-like orbit and a stable temperate climate. But the lesson from our own planet's past is that life can thrive under conditions we might consider extreme. A planet with a significant axial tilt, leading to extreme seasonal light cycles, could still be a candidate for complex life, as long as its climate system is capable of keeping it warm. The fossils under the ice expand our definition of what a habitable world can be. They are a testament to the sheer tenacity of life. But this story of life's incredible resilience is also accompanied by a much darker and more urgent message. While the fossils of the ancient polar worlds are a source of wonder, they are also a stark and unambiguous warning from the past. They are a case study, written in stone, that demonstrates the immense power of carbon dioxide to control our planet's climate. The science is clear. When CO2 levels in the atmosphere were high, the Earth was a hot, ice-free greenhouse world. When CO2 levels dropped, the planet cooled, and the ice caps formed. Today, by burning fossil fuels at an unprecedented rate, we are conducting a global experiment. We are forcibly pushing the Earth's atmospheric CO2 levels back up towards the levels they were during the Eocene and the Cretaceous. The fossils are a preview of what the endgame of that experiment looks like. They are a geological warning sign, a message from the deep past about the consequences of our current actions. The most immediate and obvious warning is about sea level rise. The great ice sheets of Greenland and Antarctica contain an enormous amount of frozen water. If they were to melt completely, as they have in past greenhouse periods, global sea levels would rise by a catastrophic amount over 200 feet, or about 65 meters. This is not speculation. It is a simple calculation of the volume of water currently locked up as ice. A world with Eocene-level CO2 would, over time, become a world with Eocene-level sea levels. This would mean the complete inundation of virtually every major coastal city on the planet. Places like London, New York, Tokyo, and countless others would be submerged beneath the waves. The coastlines of our continents would be redrawn, and hundreds of millions, if not billions, of people would be displaced. The alligator fossils on Ellesmere Island are, in a very real sense, a flood warning for every coastal community on Earth. The warning goes beyond just sea level rise. The ancient warm periods show us how the entire planet reorganizes itself in a high CO2 world. Ocean circulation patterns shift, weather systems become more extreme, and entire ecosystems are transformed. The lush rainforests of Antarctica and the subtropical swamps of the Arctic existed because the global climate was completely different. A return to those conditions would not just mean a warmer Arctic, it would mean a profoundly altered climate for everyone. The tropics could become dangerously hot, vast new deserts could form in the mid-latitudes, and the stable weather patterns that our agriculture depends on could be thrown into chaos. The past shows us that the Earth's climate system does not always change in a slow, linear way. It is capable of crossing tipping points, where a small amount of additional warming can trigger a rapid and irreversible shift into a new state. The disappearance of the polar ice caps is one such tipping point. The fossils are evidence that this has happened before. They are a warning that we are currently pushing the system back towards that same critical threshold. The story of Earth's warm past is therefore not just a fascinating tale of ancient history. It is the most important and relevant story for our own future. The fossils are a silent, powerful argument for taking climate change seriously. A message from our planet's own history that we ignore at our peril. And as this story unfolds, we are realizing that there are likely many more chapters waiting to be discovered. The story of the fossils under the ice is far from over. In fact, it may just be beginning. The vast majority of the land beneath the great ice sheets of Antarctica and Greenland remains a complete mystery, one of the last truly unexplored frontiers on Earth. We have only scratched the surface, finding fossils in the few small areas where ancient rocks are naturally exposed. What other lost worlds, what other strange creatures lie waiting to be discovered under 2 miles of solid ice? For a long time, the answer to that question seemed inaccessible. But now, 2 things are changing that. The first is technology. Scientists are developing new and sophisticated methods to see through the ice. They can use airborne radar to map the topography of the bedrock buried deep below, identifying hidden mountain ranges and vast subglacial lakes. They have developed advanced drilling technologies that can penetrate the entire thickness of the ice sheet and bring back core samples of the ancient rock and sediment beneath. These technologies will, in the coming decades, allow us to explore this hidden continent in a way that was previously impossible. But the second and more ironic factor is climate change itself. As our planet warms, the polar ice sheets are beginning to melt at an accelerating rate. Glaciers are retreating, and ice shelves are collapsing. While this is a catastrophic development for our global climate and sea levels, it is creating an unprecedented opportunity for paleontologists. As the ice melts, it is exposing ancient landscapes and fossil-bearing rocks that have been buried for millions of years. Every year, new areas of land are becoming ice-free for the first time in human history. We are entering a new golden age of polar exploration, where the retreat of the ice is likely to reveal a treasure trove of new fossil sites. What will we find? Will we find the first complete skeletons of Antarctic dinosaurs? Will we find the remains of the carnivorous predators that hunted them? Will we find fossils of ancient mammals, perhaps even primates, that lived on the continent before it froze over? The possibilities are tantalizing. The future of discovery in the polar regions is incredibly exciting. The melting ice is like a slowly opening door to a lost world. Each new fossil will add another piece to the puzzle, giving us a clearer and more detailed picture of what life was like on our planet during these ancient greenhouse periods. These future discoveries will be invaluable. They will help us to further refine our climate models, to better understand the tipping points in the Earth system, and to more accurately predict the future we are creating for ourselves. The great, frozen archives at the poles are beginning to give up their secrets. The fossils under the ice are a profound and powerful link to our planet's deep past, a story of incredible change, a warning for our future, and a promise of even more extraordinary discoveries yet to come. The Earth is speaking to us, telling us its own history, and it is a story that we are only just beginning to learn how to read. The fossils from the polar regions are a message from a different planet, a warmer, wetter version of our own world. They are a testament to Earth's incredible ability to change, and a profound warning for our own future. The secrets buried under the ice remind us that the past is never truly gone. It's just waiting to be discovered. For millions of years, the oceans were ruled by a predator of unimaginable size and power, the megalodon. This colossal shark has long been extinct, but its legend lives on through its giant fossilized teeth. Recent discoveries are now revealing new secrets about its final days and where it made its last stand. There are monsters in the deep past of our planet, creatures of such immense size and power that they challenge the limits of our imagination. In the age of the dinosaurs, the land was ruled by giants like Tyrannosaurus rex. But the reign of the dinosaurs came to a fiery end. In the oceans, however, A new dynasty of giants was just beginning. For more than 20 million years, the world seas were dominated by a single undisputed ruler, an apex predator so large and so powerful that it remains the most formidable carnivore in Earth's history. This was Carcharodon's megalodon, the giant shark known to the world simply as Megalodon. Today it is gone, a ghost that haunts the fossil record. But its legend is more powerful than ever, fueled by the incredible fossilized remains it left behind. Before we can dive into the mystery of its final days and its last refuge, we must first come face to face with the creature itself. We must reconstruct this sea monster from its fossilized remains, to understand the sheer scale of its power and the anatomy of a perfect killing machine. Our journey begins, as all stories of Megalodon must, with the only part of this magnificent creature that has survived the test of time. Our entire understanding of Megalodon, our every calculation of its size and power, is built upon a single remarkable type of fossil, its teeth. And what teeth they are! They are a testament to the brutal efficiency of a superpredator. A megalodon tooth is instantly recognizable. It is a massive, thick triangle of fossilized enamel and dentin, often larger than a human hand. The largest authenticated specimens measure over 7 inches, or 18 centimeters, in length along the diagonal. They are broad at the root and taper to a sharp, menacing point. And most importantly, the two cutting edges are lined with fine, regular serrations, like the edge of a steak knife. These are not the smooth, conical teeth of a predator that swallows its prey whole, like a crocodile. These are the teeth of a creature that slice through flesh. When you hold a megalodon tooth in your hand, you are holding a piece of a prehistoric guillotine. The reason that teeth are almost all we have of this incredible animal is because of a fundamental aspect of shark biology. Unlike us, sharks do not have a bony skeleton. Their internal framework is made of cartilage, the same flexible material that makes up our own ears and noses. Cartilage is a soft tissue that decomposes very quickly after death, and very rarely fossilizes. The only hard, mineralized parts of a shark's body are its teeth and, occasionally, the small granular structures in its skin called dermal denticles, and the solid, calcified centers of its vertebrae. This means that we have never found, and will likely never find, a complete fossil skeleton of a megalodon. The image of a massive, fully articulated shark skeleton in a museum is a scientific fantasy. Instead, the story of Megalodon has to be pieced together from a global collection of its most durable parts. Fortunately for us, sharks produce and shed teeth in incredible numbers. A shark has multiple rows of teeth in its jaw, and as the teeth in the front row become worn or broken, they fall out and are replaced by new sharp teeth moving forward from the rows behind, like a conveyor belt of daggers. A single shark can shed tens of thousands of teeth in its lifetime, and Megalodon existed for over 20 million years, dominating every ocean on the planet. The result is that the ocean floor and the fossil-bearing coastal sediments of the world are seeded with an almost unbelievable number of these giant fossilized teeth. They are found by divers in rivers in Florida, by fishermen dredging the seabed off the coast of the Carolinas, and by fossil hunters in the deserts of Peru. Each tooth is a clue, a single durable piece of a creature that was otherwise as ephemeral as the water it swam through. And by studying these millions of clues, scientists have been able to reconstruct the size and power of the monster that once wielded them. So, how do you reconstruct an animal that is more than 50 feet long when all you have is a 7-inch tooth? This is one of the great challenges and triumphs of paleontology. The process is a form of scientific detective work, based on a single crucial point of reference: Megalodon's closest living relative. For a long time it was thought that Megalodon was a direct ancestor of the modern great white shark, Carcharodon carcharias. They both have large, triangular, serrated teeth, and for many years, Megalodon was placed in the same genus as Carcharodon megalodon. However, More detailed analysis of the fine structure and evolutionary origin of the teeth has changed this view. Scientists now believe that the great white is from a different evolutionary lineage, and that Megalodon belongs to the extinct genus Carcharodonts. This is a case of convergent evolution, where two different species independently evolve similar features to adapt to a similar lifestyle, in this case being a large shark that preys on marine mammals. But even though they are not direct relatives, the great white shark remains our best modern analog. It is the closest thing we have to a living megalodon, a blueprint that we can use to scale up and estimate the size of its extinct cousin. The method involves a simple but powerful correlation. In modern sharks, there is a direct, measurable relationship between the size of a shark's teeth and its total body length. By studying hundreds of great white sharks, scientists have developed a set of reliable mathematical formulas. If you have a tooth of a certain height, you can calculate with a reasonable degree of accuracy the overall length of the shark it came from. When scientists apply these formulas to the largest known megalodon teeth, the numbers they get are staggering. The most conservative and widely accepted estimates suggest that an average adult megalodon was between 40 to 50 feet long, about 12 to 15 meters. A large, exceptional individual, the owner of a 7-inch tooth, could have reached lengths of up to 60 feet, or about 18 meters, and possibly even more. To put that in perspective, a 60-foot shark is the length of a standard bowling lane, or 3 great white sharks lined up end to end. It would have weighed an estimated 50 to 60 tons, perhaps as much as 100 tons, making it as heavy as a herd of elephants. This was not just a big shark. This was a predator on a scale that is difficult for us to even comprehend. It was the largest and most powerful vertebrate predator in the history of our planet, dwarfing even the mighty Tyrannosaurus rex in both length and mass. The reconstruction of this giant from its teeth alone is a triumph of scientific inference, a process that allows us to see the shadow of the monster, even if its body has long since turned to dust. And with its immense size came a power that was truly off the charts. An animal of such colossal size would have needed an equally colossal amount of power to function. And the evidence from Megalodon's teeth and the biomechanical models of its skull suggest that it possessed a bite force that was, quite simply, in a class of its own. To understand this, scientists have used advanced computer modeling, the same kind of finite element analysis used to understand the power of a Smilodon's fangs. They begin by creating a high-resolution 3D scan of a fossilized megalodon tooth. They then reconstruct the jaw, using the jaw of a great white shark as a template, and scaling it up to the immense proportions required for a 60-foot animal. They add in the muscles, estimating their size and power based on the attachment points and the overall size of the skull. The result is a virtual megalodon jaw, a digital crash test dummy that they can use to simulate the act of biting. When they run these simulations, the numbers that emerge are almost unbelievable. The results show that Megalodon could have generated a bite force of up to 40,000 pounds per square inch psi. For comparison, the bite force of a modern lion is about 1,000 psi. A great white shark, famous for its powerful bite, tops out at around 4,000 psi. Even the mighty T-Rex, long thought to be the champion of bite force, is estimated to have had a bite of around 12,000 psi. Megalodon's bite was more than 3 times more powerful than that of a T-Rex. What could it do with this incredible power? The answer lies in the fossils of its prey. Paleontologists have found the fossilized bones of Pliocene-era whales with huge, telltale bite marks on them. These marks, often found on rib cages and shoulder blades, are giant gouges in the bone, and the spacing of the serration marks left behind perfectly matches the teeth of a megalodon. This is the smoking gun, the direct evidence of these giant sharks in the act of hunting. And the nature of these wounds tells us about their hunting strategy. A great white shark often attacks a seal or a sea lion with a single massive bite to the soft, fleshy underbelly. Megalodon's strategy appears to have been one of pure, unadulterated brute force. It didn't need to be precise. With a bite force of 40,000 psi, it didn't attack the soft tissue, it attacked the bone. The simulations, backed up by the fossil evidence, suggest that a megalodon could have driven its serrated teeth straight through the rib cage of a small whale, puncturing the heart and lungs and causing a catastrophic, instantly fatal injury. For larger prey, its strategy was likely to immobilize it first. It would use its immense power to bite off a whale's flipper, or to shatter its tail fluke, rendering the animal helpless in the water before moving in for the kill. This was a predator that didn't just hunt, it annihilated. Its jaws were a biological wrecking ball, capable of crushing bone and shearing through flesh with terrifying ease. This almost unimaginable power allowed Megalodon to dominate its environment and to spread to every corner of the globe. The final piece of the puzzle in understanding the reign of this apex predator is its incredible global distribution. This was not a creature confined to a single ocean or a specific region. The fossilized teeth of Megalodon have been found, quite literally, all over the world. They have been dredged from the deep waters off the coast of Japan, found in the phosphate mines of Morocco, discovered in the deserts of Australia, and picked from the riverbeds of the southeastern United States. They are found from the cold waters of Denmark to the tropical coasts of Panama. This vast, cosmopolitan distribution tells us that Megalodon was an incredibly successful and adaptable species, capable of thriving in a wide range of marine environments, from cool temperate waters to the warm seas of the tropics. For over 20 million years, from the early Miocene to the late Pliocene, there was not a single ocean on planet Earth that was safe from this superpredator. It was the undisputed king of the sea, the top of every marine food chain. This global distribution also tells us something crucial about its lifestyle. To sustain a body of such immense size, Megalodon would have needed to consume a huge amount of food, an estimated 2 tons of flesh every single day. To find this much food, it would have had to have been a highly mobile, wide-ranging hunter, constantly on the move, following the great migratory routes of its primary food source, the whales. The Pliocene oceans were teeming with a rich diversity of whales, particularly medium-sized baleen whales, which were slower and less agile than many modern species. These were the perfect prey for a giant shark. The global distribution of Megalodon teeth almost perfectly mirrors the known fossil distribution of these ancient whales. Megalodon was a specialist whale hunter, and it followed its prey across the globe. This image of a global hunter completes our initial portrait of this incredible animal. We have a predator of almost unbelievable size, armed with the most powerful bite in history, and a worldwide range that made it the master of every ocean. For millions of years, it was the ultimate success story, an animal perfectly adapted to its world and its role as the apex predator. It seems almost inconceivable that such a dominant and successful creature could ever disappear. And yet it did. The story of its decline and eventual extinction is one of the great mysteries of the deep past, a mystery whose clues are now being dredged up from the dark, cold waters of its last known refuge. We have built a portrait of the Megalodon, a sea monster of almost unimaginable size and power. With its 60-foot length, its bone-crushing bite, and its global dominion over the ancient oceans, it was the undisputed apex predator for more than 20 million years. Its success seems absolute, its reign eternal. But no dynasty lasts forever. The story of Megalodon is not just one of power, but also one of decline and eventual extinction. To understand this final chapter, we must become detectives, searching for clues not just to how it lived, but where it lived during its final desperate eons. For a long time, our picture of the Megalodon's world was painted with a very broad brush. But now new discoveries, many of them dredged up from the cold, dark depths of the ocean, are allowing us to refine that picture with incredible detail. We are beginning to identify the specific environments where this giant shark made its last stand. This is the next stage of our investigation, a dive into the final habitats of the Megalodon, A journey to its last known refuges, a story that begins with a new clue brought up from the abyssal depths of the Pacific. Our story of the megalodon's final days is being constantly updated by new and exciting discoveries. The science of this ancient shark is not static. It is a dynamic field where a single new find can challenge decades of established theory. One such discovery, symbolic of this new wave of research, comes from the vast and deep waters of the Pacific Ocean. In recent years, deep-sea exploration vehicles and remote dredging operations have been exploring the abyssal plains and seamounts, thousands of feet below the surface. These operations, often searching for valuable mineral crusts, sometimes bring up unexpected treasures. In one such dredge, from a remote seamount off the coast of North America, a massive, perfectly preserved megalodon tooth was recovered. Finding a megalodon tooth is not, in itself, rare. But finding one in this specific context in a deep ocean environment, far from the shallow coastal waters where most fossils are found, is incredibly significant. This was not a fossil that had been washed out to sea from a coastal deposit. The geological context and the manganese coating on the tooth indicated that it had been lying on that deep-sea floor for millions of years. It was found where the shark had died. This single tooth and others like it that are now being found in similar deep-water locations around the world acts as a crucial new clue. It challenges our traditional understanding of where these giant sharks lived, especially towards the end of their reign. It suggests that our search for the megalodon's story needs to move away from the shallow, sunny waters we always imagined and into the darker, deeper, and more mysterious parts of the ocean. These deep-water fossils are like signposts, pointing us towards the final habitats, the last refuges where the world's greatest predator fought its final, losing battle for survival. They are forcing us to re-examine the entire life cycle of this incredible animal and to understand how its world was shrinking around it. To appreciate the significance of this shift to deeper waters, we must first understand where the megalodon began its life. The life story of a megalodon, like that of many modern sharks, began not in the deep, open ocean, but in the relative safety of a nursery. A nursery, in the biological sense, is a specific habitat where the young of a species can grow and develop. These areas typically offer two key advantages: an abundance of food and a relative lack of large predators. For a baby megalodon, this was absolutely crucial. While an adult megalodon was the undisputed king of the sea, a newborn pup was much more vulnerable. A baby megalodon was born a giant, already measuring an estimated 6 to 10 feet long at birth. But in an ocean filled with other large predatory sharks, hungry marine mammals, and even its own cannibalistic relatives, being 10 feet long was no guarantee of survival. Therefore, the mother megalodons needed to find safe, protected areas to give birth. The fossil record gives us a crystal-clear picture of where these ancient nurseries were located. For millions of years, during the warmer Miocene epoch when the species was at its peak, megalodon used shallow, warm, coastal environments as its primary birthing grounds. We have found massive concentrations of small megalodon teeth, the fossilized milk teeth of the juvenile sharks, in specific geological formations around the world. The Gatun Formation in Panama is one famous example. Here, paleontologists have found a huge number of small megalodon teeth, alongside the fossils of the small fish and marine mammals that these young sharks would have been preying on. Another key nursery site is the Bone Valley Formation in Florida, and the coastal plains of Maryland and the Carolinas in the United States. These areas during the Miocene were shallow subtropical coastal seas, filled with rich estuaries, mangrove forests, and coral reefs. They were teeming with life. The warm, productive waters would have supported huge populations of small fish, sea turtles, dugongs, and small cetaceans like dolphins and porpoises. This was the perfect environment for a young megalodon. The food was plentiful and of a manageable size, and the shallow, sometimes complex waters would have offered some protection from the larger predators, including adult megalodons, that tended to patrol the deeper offshore waters. For millions of years, this strategy was incredibly successful. These warm, shallow nurseries were like giant, oceanic kindergartens, churning out generation after generation of young megalodons that would grow up to dominate the world's oceans. The abundance of these nursery sites all over the globe was a key factor in the species' long-term success and its worldwide distribution. But this successful strategy had a critical weakness. It was entirely dependent on the existence of these specific warm, shallow coastal habitats. The entire reproductive cycle of the world's largest predator was tied to a type of environment that is highly sensitive to changes in global climate and sea level. And as the planet began to cool and the world started to change, these safe, warm nurseries began to disappear. This environmental shift would have a catastrophic effect on the megalodon's ability to reproduce, and it is likely the primary reason that, in its final days, the giant shark was forced to retreat into a different, and far more challenging kind of habitat. The new fossils being found in deep water environments, like the one from the Pacific seamount, are telling a new story about the final phase of the megalodon's existence. They suggest that as the planet cooled and the shallow coastal nurseries vanished, the remaining populations of these giant sharks became more and more concentrated in a different kind of habitat, the deeper waters of the outer continental shelf and slope. This was not a choice, it was a necessity. This move to deeper, offshore waters was likely driven by one primary factor: the location of their food. An adult megalodon was a specialist whale hunter. Its immense size and energy requirements meant that it had to prey on large, high-energy, high-fat animals. And as the global climate changed, the whales were on the move. Many of the medium-sized baleen whales that had once been common in the warm coastal seas either went extinct or they adapted to the new, cooler conditions by migrating towards the poles. The polar regions, with their cold, nutrient-rich upwelling, were becoming the new, most productive feeding grounds on the planet. But this was a world that the warm water-adapted megalodon could not follow. So the giant shark was trapped. Its old hunting grounds were becoming empty, and the new hunting grounds were too cold. Its only option was to find the last pockets of resistance, the few remaining places on Earth that still had the right combination of water temperature and a reliable supply of large prey. And these places, it seems, were the deeper waters offshore. The continental shelf and slope environments would have acted as natural refuges. Here, oceanic currents would often create areas of upwelling, bringing nutrients from the deep ocean to the surface and creating localized hotspots of productivity. These hotspots would attract schools of fish, which in turn would attract the remaining populations of medium-sized whales. And where the whales gathered, the last of the megalodons would follow. So, the picture of the late-stage megalodon is not one of a vibrant, global population, but of a fragmented and struggling one. We can imagine the last prides of these giant sharks, confined to these specific offshore hunting grounds, patrolling the edges of the continental shelves, a relict population clinging to survival in a world that was becoming increasingly hostile to them. The deep-water fossil discoveries are the physical evidence of this final, desperate chapter. Each tooth dredged up from the deep sea is a tombstone, marking a place where one of the last of these giants lived and died. It paints a haunting picture of a king in exile, a ruler whose vast kingdom had shrunk to just a few remote and challenging territories. The open ocean, which had been its playground for millions of years, was now becoming its prison. And the specific nature of this final habitat tells us even more about the pressures this incredible animal was facing. By analyzing the location of these deep-water fossil finds more closely, scientists have been able to identify a very specific type of environment that seems to have been the megalodon's last preferred habitat. It wasn't just the deep ocean. The fossils are most commonly found in what is known as the transitional zone, or the bathyal zone. This is the area of the continental slope that lies between the relatively shallow waters of the coastal shelf, the neritic zone, and the vast, flat, deep abyssal plains. This zone is typically found at depths ranging from about 200 meters to 2,000 meters. This is a dynamic and unique environment. It is the borderland between two different worlds. Here, the seafloor drops away steeply into the abyss. This topography often creates powerful currents and upwellings, which, as we've seen, make these areas highly productive oases of life in the open ocean. For a predator like Megalodon, this transitional zone would have been the perfect hunting ground in a cooling world. It would have acted as a natural funnel, concentrating the remaining populations of whales and other large marine mammals as they migrated along the edges of the continents. A megalodon could have patrolled these slopes, using the steep drop-off to its advantage, perhaps ambushing its prey from the deep, dark water below. The fossils found in these zones tell a story of a creature pushed to the edge, both literally and figuratively. It had been forced out of its comfortable coastal nurseries and was now living a more challenging pelagic existence, hunting along these deep-water corridors. This habitat shift would have come with new challenges. The water was cooler, requiring the shark to expend more energy to maintain its body temperature. The prey may have been more scarce and spread out, requiring longer and more energy-intensive hunting expeditions. And the young, if they were still being born in this environment, would have faced even greater dangers, with no shallow water refuges to protect them from the predators of the open ocean, including their own kind. The picture that emerges is one of a species under immense environmental stress. The transitional zone was not a paradise. It was a refuge, a place of last resort. It was the only environment left that provided the specific conditions, the right temperature and a critical mass of large prey that a 60-ton superpredator needed to survive. The concentration of teeth in these specific deep-water locations around the world, from the Blake Plateau off the coast of the Carolinas to the seamounts of the Pacific, allows us to draw a map of the megalodon's final kingdom. It was not a continuous global empire, but a series of isolated deep-water pockets of survival. These were the last battlegrounds in the megalodon's long war against extinction. For a time, perhaps for a few 100,000 years, this strategy worked. The giant shark managed to cling on in these deep-water refuges. But the forces of global change were relentless. The planet continued to cool, the ice caps continued to grow, and the ocean ecosystems continued to transform. The transitional zone habitat, which had been its lifeline, was itself a transient feature. As the world changed around it, even this last refuge would eventually fail, and the reign of the world's greatest predator would finally come to a definitive and final end. The clues from the deep have given us a haunting and intimate glimpse into this process, allowing us to witness the slow, inexorable decline of a giant, as it was pushed further and further into the dark, cold abyss. The new fossil discoveries from the deep ocean have given us a haunting glimpse into the final chapter of the megalodon's reign. We have seen how this once global ruler was pushed out of its comfortable coastal nurseries and forced into a handful of deep-water refuges, a king in exile. But this raises the ultimate question. What was it running from? What powerful forces were at play that could possibly threaten, and ultimately destroy, a 60-ton superpredator with the most powerful bite in history? The extinction of the megalodon was not a single sudden event. It was a slow, agonizing decline, a death by 1,000 cuts, driven by a series of profound and interconnected environmental changes that completely reshaped the world's oceans. To understand the giant's demise, we must now investigate the crime scene. We must reconstruct the collapsing world of the Pliocene epoch, following the chain of cause and effect that led to the disappearance of this magnificent creature. Our investigation begins with the great global thermostat, the force that would set in motion a catastrophic cascade of events, the cooling of the planet. The long reign of the megalodon for most of the Miocene epoch took place in a world that was significantly warmer than our own. It was a hothouse world, with higher sea levels and warm, tropical waters extending much further towards the poles. This was the perfect environment for a large, warm water-loving shark. But starting around 5 million years ago, in the Pliocene epoch, the Earth's climate began to change dramatically. The planet entered a new phase of global cooling. This was a natural process, driven by a combination of factors, including subtle shifts in the Earth's orbit, the ongoing movement of the continents, and a gradual natural decrease in atmospheric carbon dioxide levels. This cooling trend had its most dramatic effect at the poles. For the first time in millions of years, a permanent ice cap began to form over the Arctic. The Great Antarctic Ice Sheet, which had already begun to form earlier, now expanded dramatically. The planet was transitioning from a greenhouse state to the icehouse world we know today. This global cooling was the primary driver, the first domino to fall in the chain of events that would lead to the megalodon's extinction. The direct effect of the cooler water temperatures would have been a significant challenge for the giant shark. While megalodon was likely partially warm-blooded, a phenomenon known as regional endothermy, which we see in modern great white sharks, allowing it to maintain a body temperature higher than the surrounding water, there were limits. A creature of that immense size would have had to expend a huge amount of metabolic energy just to stay warm in a cooling ocean. This would have increased its already massive daily calorie requirement, putting even more pressure on it to find food. But the indirect effects of this global cooling were far more catastrophic. The cooling of the oceans didn't just make the water colder. It fundamentally re-engineered the entire marine ecosystem, from the smallest plankton to the largest whales. The world that megalodon had evolved to dominate was beginning to disappear. And the first and most devastating casualty of this change was the shark's primary food source. A superpredator is nothing without its prey. The megalodon was a highly specialized hunter, and its main target was the rich and diverse community of whales that populated the Miocene and Pliocene oceans. The fossil record shows us that during megalodon's peak, the seas were teeming with a wide variety of medium-sized baleen whales, creatures like Cetatherium. These whales were, in many ways, the perfect prey. They were relatively small, typically between 15 to 30 feet long, making them a manageable size even for a single megalodon. They were also relatively slow swimmers compared to the massive, fast-moving rorqual whales, like the blue whale or the fin whale, that dominate the oceans today. And most importantly, they were abundant and found in the warm, productive coastal and offshore waters that the megalodon preferred. These whales were the bison of the sea, and megalodon was the wolf that hunted them. For millions of years, this predator-prey relationship was in balance, and it fueled the success of the giant shark. But the global cooling of the Pliocene threw this entire system into chaos. As the poles froze and the temperature difference between the equator and the poles increased, the ocean circulation patterns began to change. Powerful nutrient-rich upwellings began to appear in the high latitudes, creating incredibly productive new feeding grounds in the cold polar and subpolar waters. This created a powerful new evolutionary pressure on the whales. Many of the old, slow-swimming baleen whale species, which were adapted to the warm, stable waters of the Miocene, could not cope with these changes and simply went extinct. Other whale lineages, however, adapted and thrived. They evolved much larger body sizes, which is more efficient for retaining heat in cold water. They evolved new feeding strategies like the lunge feeding of modern rorquals, which allowed them to take huge gulps of krill in the productive polar seas. And, most importantly, they developed long-distance migratory behavior. They would spend the summers feeding in the incredibly rich but frigid polar waters, and then migrate to warmer, safer waters in the tropics to give birth. This was a disaster for the megalodon. Its entire food supply was either going extinct, or was moving to a new location where the giant shark could not follow. The cold polar waters would have been metabolically impossible for a warm water-adapted creature like megalodon. It was being shut out of the new, all-you-can-eat buffet at the poles. It was left behind in the now less productive tropical and temperate waters, with a dwindling supply of its traditional prey. It's like a lion on the Serengeti watching as all the wildebeest and zebra suddenly decide to migrate to Siberia for the summer. The hunter is left behind in an empty landscape. The loss of its primary food source was the single most devastating blow to the megalodon. We can see evidence of this in the fossil record. As the Pliocene progresses, the diversity of those medium-sized baleen whales plummets. At the same time, the number and distribution of megalodon teeth begin to decline. The fates of the predator and its prey were inextricably linked. As the whales disappeared, the shark began to starve. And this was not the only part of its world that was vanishing. The global cooling and the growth of the polar ice caps had another profound and direct impact on the megalodon's life cycle. It caused a massive drop in global sea levels. As vast quantities of the planet's water were locked up in the form of continental ice sheets, the level of the oceans fell, in some cases by hundreds of feet. This had a catastrophic effect on the shallow coastal environments that the megalodon depended on for its nurseries. The warm, protected, shallow water bays, estuaries and coastal seas that had served as the safe havens for young megalodons for millions of years were literally left high and dry. As sea levels fell, these areas became dry land or were transformed into much smaller, less suitable habitats. This was a critical blow to the megalodon's ability to reproduce successfully. The giant shark was now facing a double crisis. The adult hunting grounds in the open ocean were becoming empty, and the safe nursery grounds in the coastal waters were disappearing. Without these safe nurseries, the survival rate of newborn megalodon pups would have plummeted. A baby megalodon born in the deeper, open ocean would have been incredibly vulnerable. It would have been exposed to a greater number of large predators, including other sharks, pods of killer whales, and even adult megalodons, which were likely cannibalistic as many modern sharks are today. Finding enough food of the right, smaller size would also have been much more difficult in the less productive offshore waters compared to the teeming life of a coastal estuary. The reproductive cycle of the species was broken. It was becoming increasingly difficult for the adults to find enough food to survive, and it was becoming increasingly difficult for the young to survive to adulthood. The population was being squeezed from both ends. The decline, which may have started with the adults struggling for food, would have been massively accelerated by this reproductive failure. The species was no longer able to replenish its numbers effectively. It was an aging and shrinking population, a dynasty in its final terminal decline. And as if these environmental pressures weren't enough, the struggling megalodon was now about to face a new and formidable rival, a smaller, faster, and more adaptable shark that was perfectly suited to this new, cooler world. Evolution never happens in a vacuum. As one species struggles and declines, it often creates an opportunity for another to rise and take its place. As the megalodon was facing the crisis of a cooling world and a collapsing food chain, a new competitor emerged on the scene, a shark that would ultimately become the new king of the seas. The great white shark, Carcharodon carcharias. The evolutionary history of the great white is still debated, but it seems to have evolved from a lineage of smaller mako-like sharks. It was a creature perfectly adapted to the new cooler oceans of the Pliocene. While smaller than the megalodon reaching a mere 20 feet in length, the great white was a faster, more agile, and more versatile predator. Its smaller size meant it had a lower overall energy requirement, so it could survive on smaller and more varied prey. It was not solely dependent on large whales. A great white could happily hunt seals, sea lions, dolphins, and large fish. It was a generalist, not a specialist. This adaptability was its greatest strength. As the large whales disappeared, and the megalodon began to starve, the great white was able to thrive by switching to the smaller marine mammals that were still abundant. A crucial point of competition would have been the juvenile megalodons. A young 10-foot-long megalodon would have been in direct competition for the same food as an adult great white, and the great white was likely a more efficient and agile hunter of this smaller prey. Furthermore, an adult great white would have been a direct predatory threat to a young megalodon. It is very likely that great whites actively hunted the vulnerable megalodon pups, further devastating their already failing reproductive success. The rise of the great white shark was the final fatal blow to the megalodon. It was being outcompeted and preyed upon by a smaller, more adaptable rival. The old king was being overthrown. The megalodon, a specialist of a warm, stable world, was an evolutionary relic, a dinosaur of the seas. The great white, a nimble generalist of a cooler, more dynamic world, was the future. This combination of factors created a perfect storm of extinction. It was not a single event, but a slow, grinding, and inevitable process. First, the cooling climate began to change the rules of the game, re-engineering the ocean currents and temperatures. Second, this led to the collapse and migration of the megalodon's primary food source, the medium-sized whales, effectively starving the giant predator. Third, the falling sea levels eliminated the vital nursery habitats, causing a catastrophic reproductive failure. And finally, the rise of a new, more adaptable competitor in the form of the great white shark applied the finishing blow, outcompeting the struggling giant for the remaining resources. The world had changed, and the megalodon simply could not change with it. Its incredible size and power, once its greatest assets, now became its greatest liabilities in this new, leaner, and colder world. The disappearance of the megalodon is therefore not a mystery in the sense of an unsolved crime. It is a powerful and tragic lesson in evolutionary biology, a clear example of how even the most dominant and successful species can be driven to extinction when its environment changes beneath it. The king was dead, a victim not of a single assassin, but of a global conspiracy of climate, prey, and a smaller, more cunning rival. The case against the megalodon seems closed. A perfect storm of climate change, disappearing prey, lost habitats, and a new formidable rival all conspired to bring the reign of the giant shark to an end. The evidence for its extinction is overwhelming. But within this larger story, there are still fascinating and fiercely debated questions, mysteries that scientists are continuing to unravel with each new fossil discovery. The final chapter of the megalodon story is not just about why it disappeared, but also about the precise details of how and when it took its final bow. This is where the science gets truly interesting, as researchers sift through the fossil evidence, reevaluate old assumptions, and try to pinpoint the exact moment that the world's greatest predator vanished forever. This is the final extinction debate, a series of crucial questions that take us to the very edge of the megalodon's existence and beyond. The first and most fundamental of these questions is, when did the last megalodon actually die? For many decades, the accepted date for the extinction of the megalodon was approximately 2.6 million years ago. This date was significant because it marked the boundary between two geological epochs, the Pliocene and the Pleistocene. The beginning of the Pleistocene was marked by a dramatic intensification of the global cooling trend, the point at which the great ice ages truly began to take hold in the northern hemisphere. This seemed like a very neat and tidy explanation. The world got much colder, and the megalodon, a warm water creature, died out. This date was cited in textbooks, documentaries, and museum exhibits for years. It was based on the dating of the youngest known megalodon fossils found in the geological record. But science is a self-correcting process. And in recent years, a new generation of scientists has gone back to re-examine the evidence for this 2.6 million-year-old extinction date, and they have found some serious problems. A team of researchers undertook a massive project to re-evaluate every single documented megalodon fossil from the late Pliocene and early Pleistocene. They looked at fossils in museum collections all over the world. What they discovered was that many of the fossils that had been dated to this younger period were problematic. Some of them had been misidentified. They were not megalodon teeth at all, but perhaps the teeth of a large great white or another extinct shark. Others came from reworked fossil deposits. This is a common problem in paleontology. A fossil can erode out of an older rock layer, be washed down a river, and then be redeposited in a much younger layer of sediment. If you then date the younger layer, it can give you a false, much younger age for the fossil itself. It's like finding a Roman coin in the foundations of a modern building and concluding that the Romans were still minting coins today. The researchers carefully filtered out all these problematic and unreliable data points. When they were left with only the fossils whose age and identity could be verified with a high degree of confidence, a new and very different picture emerged. All of the reliable, confirmed megalodon fossils were older than the 2.6-million-year-old boundary. The new analysis concluded that the true extinction of the megalodon happened much earlier, around 3.6 million years ago. This might seem like a small academic adjustment, but it is a hugely significant change in the story. Pushing the extinction date back by a full 1 million years changes our understanding of what killed it. It means that the megalodon was already gone long before the most intense phase of the Ice Age cooling began. This suggests that the final dramatic plunge in temperature was not the killer. Instead, the shark's decline was a more drawn-out and complex affair, driven by the earlier, more gradual cooling of the Pliocene and the associated collapse of its food web. It means that the rise of the great white shark as a major competitor likely played an even bigger role than previously thought. The new extinction date of 3.6 million years ago is now becoming the new scientific consensus. It paints a more nuanced picture of a long, slow decline rather than a single catastrophic final event. But even with this revised timeline, the discovery of new fossils in unexpected places continues to raise tantalizing questions. The new extinction date of 3.6 million years ago seems solid, based on the reliable fossil record. But this is where the new discoveries of megalodon teeth in deep ocean environments add a fascinating and speculative new wrinkle to the story. These deep water fossils found in the shark's last refuges have led some to ask a tantalizing question. Could isolated populations of megalodon have survived for longer than we think? Is it possible that the fossil record from the shallower coastal areas, which is what most of our data is based on, is telling an incomplete story? The hypothesis goes like this. As the megalodon's world collapsed, the vast majority of the global population did indeed die out around 3.6 million years ago. However, a few small relict populations might have managed to cling on for much longer in those specific deep-water hotspots, where their whale prey was still available. These deep ocean refuges, with their unique currents and stable conditions, might have acted like oceanic life rafts, allowing the last of the giants to survive for hundreds of thousands of years after the rest of their kind had vanished. This is a very difficult theory to prove or disprove. The deep ocean is the largest and least explored environment on Earth, and its fossil record is incredibly sparse and difficult to access. A small, dwindling population of sharks living in this vast expanse would leave behind very few fossils, and the chances of us finding one are astronomically small. So, the absence of evidence is not necessarily evidence of absence. However, most mainstream scientists remain highly skeptical of this late survival hypothesis. They argue that a viable breeding population of a 60-foot predator, even a small one, would still have a significant ecological impact and would leave behind more evidence than we have found. For a species to survive, you need more than just a few last individuals. You need a large enough gene pool to avoid inbreeding and to weather any further environmental changes. It is far more likely, they argue, that the deep ocean fossils we are finding are not from a later, surviving population, but are simply from the final populations that existed before the 3.6-million-year-old extinction event. They are fossils from the last act of the play, not from a secret encore performance. While the idea of a few last megalodons surviving into a later epoch is a romantic and exciting thought, the current evidence does not support it. The deep-water fossils are not telling us that the shark survived for longer. They are showing us where it made its final stand. This leads us to another key question that the fossil discoveries are helping to answer. Why are megalodon teeth so incredibly common in certain specific locations around the world, while being completely absent in others? You can search for a lifetime in some marine fossil beds and never find a single megalodon tooth. But in other places like the rivers of South Carolina, the phosphate mines of Florida, or certain deep-sea dredge sites, you can find them in huge numbers. These concentrations of teeth are not random. They are archaeological clues, mapping out the key hubs of the megalodon's world. The reason for these concentrations goes back to the shark's life cycle and its final shrinking habitats. The famous fossil beds in Florida and the Carolinas are so rich in teeth because they were the locations of the ancient coastal nurseries. For millions of years, generation after generation of megalodons were born, grew up, and shed their teeth in these specific areas. These places became giant, natural repositories for juvenile teeth. The newer discoveries, the concentrations of teeth being found in deep water locations, are telling a different story. These are not nurseries. They are the final hunting grounds. The reason so many teeth are found in these specific offshore locations is because these were the last cafes on the highway, the few remaining places where the last populations of adult megalodons were congregating to hunt the last of their whale prey. The sharks would have spent most of their time in these productive hotspots, and over thousands of years, the teeth they shed would have rained down onto the seafloor below, creating a dense fossil record of their final presence. So when divers find a rich deposit of megalodon teeth in a deep river channel, or when a research vessel dredges up a collection of them from a seamount, they are not just finding fossils. They are, in a very real sense, discovering the precise location of one of the megalodon's last refuges. They are mapping the geography of an extinction. Each concentration of teeth is a pin on the map, showing us the shrinking boundaries of the giant's world. This allows us to reconstruct the final days of this species with incredible detail, to see how a once global empire collapsed into a few, isolated pockets of survival before winking out entirely. And this finality, this certainty of extinction, leads us to the last, and perhaps most popular question of all. No discussion of the megalodon would be complete without addressing the question that dominates popular culture, fuels sensationalist television shows, and keeps the legend of this creature alive in the public imagination. Could it still be alive today? Could this giant predator have survived in the vast, unexplored depths of the ocean? A true sea monster hiding from the prying eyes of science? The idea is tantalizing. The ocean is immense and mysterious, and we have explored only a tiny fraction of it. We are constantly discovering new species in the deep sea. So, is it possible that a 60-foot super predator could have eluded us? The scientific answer, despite what you might see on TV, is a clear, definitive, and resounding no. There are several powerful lines of evidence that make the survival of the megalodon into the modern day a biological impossibility. The first is the fossil record itself. As we've seen, the reliable, verifiable fossil evidence for megalodon disappears completely around 3.6 million years ago. There is not a single authenticated megalodon tooth, jaw, or vertebra that is younger than this. For it to have survived, it would have had to live for 3.5 million years without leaving a single trace in the fossil record. A statistical impossibility for a creature that shed tens of thousands of teeth in its lifetime. The second line of evidence is ecological. An animal the size of a megalodon would be an apex predator with a massive metabolic rate. It would need to eat constantly, and it would have a huge impact on its environment. We would see its ecological footprint. The most obvious sign would be its bite marks. If megalodons were still patrolling the oceans, we would expect to find modern whales, blue whales, humpbacks, sperm whales washing up on beaches with the characteristic, giant, serrated bite marks of a megalodon attack. No such evidence has ever been found. The bite marks we do see on whales come from other known predators, like great whites and orcas. The absence of these telltale wounds on modern marine life is deafeningly silent proof of the megalodon's absence. Finally, there is the simple fact of its preferred habitat and food. We know that Megalodon was a creature of warm and temperate waters, and it was a specialist whale hunter. The ocean environment that it was adapted for largely disappeared millions of years ago. Its primary food sources went extinct. The idea that it could have somehow survived this complete collapse of its world, perhaps by adapting to a new life in the cold, dark, and food-poor abyss, goes against everything we know about its biology. It was a warm water specialist, and its world is gone. So while the myth of a living megalodon makes for exciting entertainment, it has no basis in scientific reality. The giant is well and truly extinct. Its story is not one of mysterious survival, but of a well-documented and understood extinction. The real mystery of the megalodon is not whether it is still alive, but how we can use its incredible story to better understand the deep history of our planet. The final extinction debate shows us how science works, how new discoveries can refine and change our understanding, and how we can piece together the story of a lost world from the smallest of clues. The megalodon's legacy is not in the murky depths of the modern ocean, but in the millions of magnificent fossilized teeth it left behind, each one a tangible connection to the awesome and terrifying power of the ancient seas. The megalodon was the undisputed king of the ancient seas, a predator of awesome power. The latest fossil discoveries give us a haunting glimpse into its final days, a story of a giant struggling to survive in a changing world. It is a powerful reminder that no ruler, no matter how dominant, reigns forever. In the vast, windswept plains of Patagonia, scientists have found something more intimate than bone: the fossilized footprints of the giants who once ruled this land. These are not just fossils, they are frozen moments in time, revealing the secret lives of colossal sauropods and the terrifying theropods that hunted them. The story of the dinosaurs is most often told through their bones. We marvel at the colossal skeletons assembled in museum halls, the fossilized remains that give us a blueprint of their anatomy, their size, and their power. These bones are the essential foundation of our knowledge, but they are a static record. They tell us what these creatures were, but they rarely tell us what they did. To understand the lives of the dinosaurs, to see them not just as skeletons but as living, breathing animals, we need a different kind of evidence, a more intimate and ephemeral trace of their existence. We need to find their footprints. A footprint is a magical thing. It is a single frozen moment in time, a direct record of an animal interacting with its environment. And in the vast, windswept, and hauntingly beautiful landscapes of Patagonia, at the southern tip of South America, scientists have discovered a treasure trove of these frozen moments. Here, the story of the dinosaurs is written not just in bone, but in the very ground they walked upon. This is the story of the giants of Patagonia, a land where the earth itself remembers their steps. Our story is set in a region that has become, in the last few decades, the undisputed epicenter of dinosaur paleontology. Patagonia, a vast and sparsely populated territory shared by Argentina and Chile, is a land of dramatic landscapes, from the towering peaks of the Andes to the arid steppe-like plains that stretch for hundreds of miles. But beneath this modern landscape lies another, much older one. During the late Cretaceous period, from about 100 million to 66 million years ago, Patagonia was a very different place. It was a key part of the great southern supercontinent, Gondwana, and it was a world teeming with some of the most spectacular dinosaurs that have ever lived. So why Patagonia? What is it about this specific region that has made it such a goldmine for paleontologists? The answer lies in a perfect combination of geological circumstances. Firstly, the rocks in many parts of Patagonia are of the exact right age. The sedimentary layers exposed by wind and water erosion date precisely to the late Cretaceous, the final act in the age of the dinosaurs. These layers, ancient river floodplains, coastal estuaries, and inland basins were the perfect environments for preserving the remains of the animals that lived and died there. Secondly, the modern climate of much of Patagonia is arid and sparsely vegetated. This is crucial for fossil hunting. In a lush, forested environment, fossils are hidden beneath a thick blanket of soil and plants. But in the dry, windswept plains of Patagonia, the relentless wind and occasional rain are constantly eroding the rock, exposing new fossils on the surface. Paleontologists can literally walk across the landscape and spot the telltale fragments of fossilized bone weathering out of the ground. It is one of the few places on Earth where you can find the remains of colossal dinosaurs lying exposed on the surface. And finally, the sheer scale of the place is a factor. Patagonia is immense, and much of it remains unexplored. Every year, new expeditions venture into remote areas and discover new fossil sites, each one adding another piece to the puzzle of this lost world. It is this unique combination of the right rocks, the right climate, and vast, unexplored territory that has made Patagonia the land of giants, the place where our understanding of the upper limits of dinosaur size has been completely rewritten. And the most famous of these giants are the colossal, long-necked sauropods. If Patagonia is the land of giants, then the titanosaurs are its undisputed kings. The titanosaurs were the last and the largest group of the sauropod dinosaurs, the long-necked, long-tailed, plant-eating quadrupeds that were the biggest land animals in Earth's history. And Patagonia was their global headquarters. It is here that the fossilized remains of the true giants of this group have been discovered. For many years, the record for the largest known dinosaur was held by creatures from North America, like Diplodocus and Brachiosaurus. But in the 1990s and 2000s, a series of incredible discoveries in Patagonia shattered all previous records. In 1993, the discovery of Argentinosaurus was announced. The fossils were fragmentary, consisting mainly of a few colossal vertebrae, ribs, and a leg bone. But the size of these bones was staggering. A single vertebra was over 5 feet tall. Based on these remains, paleontologists estimated that Argentinosaurus could have reached a length of over 100 feet, about 30 meters, and weighed somewhere between 70 and 100 tons. It was, at the time, the heaviest land animal ever discovered. For years, Argentinosaurus held the title. But then, in 2014, a sheep rancher in another part of Patagonia stumbled upon another fossil graveyard of even more incredible proportions. An expedition to the site uncovered a massive collection of over 200 fossilized bones belonging to at least 6 different individuals of a new, even larger species of titanosaur. The centerpiece of the find was a femur, a thigh bone that measured nearly 8 feet long. When stood on end, it was taller than a person. This new creature was given the fitting name Patagotitan mayorum, the Patagonian titan from the Mayo family, who owned the ranch. Based on these more complete remains, scientists were able to calculate its size with greater accuracy. Patagotitan was estimated to be around 122 feet long, 37 meters, and to weigh close to 70 tons. It was longer than a blue whale, the largest animal alive today, although not as heavy. These Patagonian titans force us to confront the sheer scale of life in the late Cretaceous. They were walking, breathing ecosystems, creatures so large that the ground must have trembled when they walked. Their immense size was a successful evolutionary strategy, likely a defense against the terrifying predators with whom they shared their world. And the predators of Patagonia were equally monstrous. The natural law of any ecosystem is that where there are giant herbivores, there will be giant carnivores to hunt them. The discovery of the colossal titanosaurs in Patagonia immediately raised a tantalizing question. What could possibly prey on a 70-ton animal? The answer soon began to emerge from the same fossil beds. It turned out that Patagonia was also home to a family of giant carnivorous dinosaurs, the Carcharodontosaurids, a group of theropods that rivaled, and in some cases even exceeded, the mighty Tyrannosaurus rex in size. For a long time, T. rex from North America was considered the largest meat-eating dinosaur. But in 1995, the discovery of Giganotosaurus in Patagonia changed that. Giganotosaurus, whose name means giant southern lizard, was known from a partial skeleton, but it was enough to show that it was slightly longer and perhaps even heavier than the largest known T-Rex. It had a massive skull, over 5 feet long, filled with long blade-like serrated teeth, perfect for slicing through the flesh of giant sauropods. It was the new king. But the story didn't end there. Another, even more intriguing discovery was made at a site where the fossilized remains of multiple individuals of another giant carcharodontosaurid were found jumbled together. This new predator was named Mapusaurus. The fact that several individuals were found together has led to the incredible and terrifying possibility that these giant killers may not have been solitary hunters, but may have hunted in cooperative packs. A single Mapusaurus would have been a formidable predator, but a pack of them working together would have been a force of nature, one of the few things on Earth capable of tackling a juvenile or even a subadult titanosaur. The discovery of these giant Patagonian predators provides the other half of the ecological equation. We now have a complete picture of the top of the food chain. Colossal herd-dwelling herbivores being stalked by equally colossal, pack-hunting carnivores. It was a world of epic life-and-death struggles, a prehistoric drama played out on a scale that is almost impossible for us to imagine. The fossil bones from Patagonia give us the cast of characters for this drama. They tell us who the players were. But bones are a record of death. To understand the story of their lives, we need a different kind of fossil, a record of their actions. While the skeletons of the giant dinosaurs of Patagonia are spectacular, they represent only one part of the fossil record. In recent years, another, equally important type of fossil evidence has come to the forefront of research in the region: the fossilized footprints of the dinosaurs themselves. A fossil footprint, or a trackway of multiple prints, is a form of trace fossil. It is not a part of the animal's body, but it is a direct record of the animal's behavior. It is a snapshot of a living creature, interacting with its environment, in a way that a skeleton can never be. And Patagonia is proving to be one of the richest places in the world for these remarkable fossils. In places like the Neuquén Basin in Argentina, vast surfaces of ancient mudflats and riverbanks have been exposed, covered in the fossilized tracks of the dinosaurs that walked there 100 million years ago. These track sites are like prehistoric crime scenes, preserving the clues of who was there, where they were going, and what they were doing. How does a footprint become a fossil? It requires a very specific set of circumstances. First, a dinosaur has to walk across a surface that is soft enough to record an impression, but not so soft that the print collapses. The fine, wet mud of a lakeshore or a river floodplain is the perfect medium. Second, the print has to be preserved before it can be eroded away by wind or rain. This usually happens when it is quickly but gently buried by another layer of sediment, perhaps from a gentle flood or a sandstorm. This new layer acts as a protective cap. Over millions of years, the layers of sediment turn to rock, and the footprint is preserved as a natural mold. Later, geological uplift and erosion can expose this ancient rock surface, revealing the fossilized trackway to the eyes of a modern paleontologist. The discovery of a major track site is an incredibly exciting event. It is like finding a lost manuscript of the dinosaur's life story. By studying these tracks, a specialized field of paleontology called ichnology, scientists can deduce an incredible amount of information that bones alone could never tell us. They can learn about the posture and gait of the animals, their speed, their social structures, and their interactions with their environment. The fossil footprints of Patagonia are a different kind of treasure. A treasure not of anatomy, but of action. They allow us, for a brief moment, to walk in the footsteps of giants and to see the lost world of the Cretaceous not as a static collection of skeletons, but as a dynamic world in motion. They are the living memory of the land of the giants. The vast, windswept plains of Patagonia have given us the bones of giants. They have revealed a lost world dominated by the largest herbivores and carnivores that ever walked the earth. But as we've discovered, there is another, more intimate record of this world preserved in the ancient rock. the fossilized footprints of the dinosaurs themselves. A skeleton can tell us how a dinosaur was built, but a footprint tells us how it lived. It is a single frozen moment of action. But how do scientists read these stories in stone? How can a simple depression in the rock reveal the secrets of an animal that has been extinct for over 66 million years? The answer lies in the fascinating science of ichnology, the study of trace fossils. Ichnologists are the detectives of paleontology. They look for the clues left behind by living animals' footprints, burrows, and nests, and use them to reconstruct the behavior and lifestyles of these ancient creatures. To understand the incredible stories being revealed in Patagonia, we must first understand the methods of these detectives. We will now walk through the process of reading the tracks, a step-by-step guide to how a simple footprint can be used to resurrect a living, moving dinosaur. The first and most fundamental step is to identify who made the print. When a paleontologist first encounters a fossilized footprint, the initial challenge is to play the role of a prehistoric tracker. They must answer the question, who made this track? This process of identification is a careful science of observation and comparison. The primary clues are found in the shape, or morphology, of the footprint itself. The first major distinction they look for is between the two main groups of dinosaurs that dominated Patagonia: the giant four-legged sauropod herbivores and the two-legged theropod carnivores. A sauropod footprint is usually easy to recognize. These colossal, elephant-like animals had feet that were adapted for supporting immense weight. Their front feet, or manus, often left a large, crescent-shaped impression. Their back feet, or pies, were much larger and more rounded, sometimes almost circular with blunt, stubby toes. When you find a trackway of a sauropod, you see a pattern of these large, rounded back footprints accompanied by the smaller, crescent-shaped front footprints. It is the track of a massive, heavy four-legged walker. The footprint of a theropod predator, on the other hand, is completely different and instantly recognizable. Theropods were bipedal, meaning they walked on two legs, so you only find the tracks of their back feet. And their feet had a classic bird-like structure. A typical theropod track shows three large, forward-pointing toes, often armed with sharp, pointed claw impressions at the tips. This three-toed, or tridactyl, shape is the signature of a theropod. It is a design built for agile movement and, in some cases, for speed. By carefully examining the details of the print, scientists can often get even more specific. The size of the print, the relative length of the three toes, the angle between them, and the shape of the heel pad can all provide clues to the specific family or even genus of theropod that made the track. For example, the footprints of a giant carcharodontosaurid like Giganotosaurus would be enormous, over 2 feet long, with massive, robust toe impressions, indicating a powerful, heavy predator. In contrast, the tracks of a smaller, more agile raptor-like dinosaur would be much smaller and more slender, with a more pronounced sharp claw mark. By comparing the fossil footprints to the known foot skeletons of the dinosaurs found in the same region, scientists can make a confident identification. It's like matching a footprint at a crime scene to a suspect's shoe. This first step is crucial. It gives us our character. We now know whether we are following the trail of a giant, lumbering herbivore or a sharp-clawed, agile predator. And once we know who we are following, the next step is to figure out what they were doing. Once the track maker has been identified, the next step for the ichnologist is to bring the animal to life, to get a sense of its size and its movement. This is done by taking a series of careful measurements from the trackway. The first and most basic measurement is the size of the individual footprint. There is a direct and reliable correlation between the length of an animal's foot and its overall size, particularly its height at the hip. By measuring the length of a fossil footprint, scientists can use established formulas, derived from studying modern animals, to calculate a very good estimate of the dinosaur's hip height. For a bipedal theropod, this gives you a great sense of its overall stature. For a quadrupedal sauropod, it helps to estimate the size of its massive limbs. This is an incredibly valuable tool because it allows us to get a sense of the size of an animal, even if we don't have its skeleton. We can know how big the dinosaurs in a particular area were, just from the tracks they left behind. But the real magic happens when you have not just a single print, but a trackway, a sequence of consecutive steps made by the same individual. A trackway allows us to calculate the animal's speed. The key measurement here is the stride length, which is the distance between two consecutive footprints made by the same foot, for example, from one left footprint to the next left footprint. A long stride length means the animal was moving quickly, its legs covering a lot of ground with each step. A short stride length means it was moving slowly. By combining the stride length with the estimated hip height, scientists can plug these numbers into a biomechanical formula to calculate a surprisingly accurate estimate of how fast the dinosaur was moving. They can tell us whether the animal was engaged in a slow walk, a steady trot, or a fast run. This is where the story truly comes to life. We are no longer looking at a static footprint. We are watching a moving animal. We can determine that a giant sauropod was walking along a riverbank at a slow, leisurely pace of about 2 miles per hour. Or we can discover that a predatory theropod was moving at a brisk trot of 8 miles per hour, perhaps searching for prey. This ability to calculate speed is what allows us to see the dynamism of the prehistoric world. It transforms the trackways from simple curiosities into pages from a storybook. The spacing of the prints becomes the rhythm and tempo of the story. A trackway with evenly spaced, slow-walking prints tells a story of calm, everyday life. A trackway where the stride length suddenly increases dramatically tells a story of alarm, of an animal suddenly breaking into a run. It could be a predator starting its attack, or a herbivore fleeing in terror. The science of reading these tracks allows us to reconstruct the motion and the drama of these prehistoric scenes. We have identified our character, we know its size, and we know how fast it was moving. But to complete the picture, we need to know the setting of our story. A footprint is not just a record of an animal. It is also a record of the ground upon which that animal walked. The rock layer in which the footprints are fossilized, the substrate, holds a wealth of information about the ancient environment. This is where ichnology meets another branch of geology, sedimentology, the study of sediments and how they form rock layers. By carefully analyzing the type of rock that contains the footprints, scientists can reconstruct the ancient landscape with incredible detail. For example, if the footprints are preserved in a fine-grained mudstone or siltstone with fossilized ripple marks, it tells us that the dinosaur was walking through the soft, wet mud on the edge of a lake or a slow-moving river. We can almost feel the squish of the mud between its toes. The presence of fossilized mud cracks in the same layer might indicate that this was an environment that went through wet and dry seasons, with the mudflats drying out and cracking in the sun. If the footprints are found in a coarser sandstone, it might suggest a different environment, perhaps a sandbar in a larger, more powerful river system, or the dunes of an ancient desert. If the tracks are associated with the layer of coal or fossilized plant material, it tells us that the dinosaur was walking through a swampy, densely vegetated area. The sedimentology provides the context, the setting for our prehistoric drama. It tells us whether our sauropod was walking along a placid lakeshore or crossing a vast, arid floodplain. This is crucial for understanding the animal's ecology. It shows us the specific habitats that these dinosaurs preferred. We can learn that certain types of sauropods seem to spend most of their time in coastal estuarine environments, while certain theropods may have preferred the more open inland plains. This helps us to build a more complete and nuanced picture of the entire ecosystem, to see how the different species were distributed across the landscape, and how they interacted with their specific environments. The preservation of the footprint itself can also tell us about the condition of the ground. A deep, well-defined print with mud pushed up around the edges indicates a very soft, wet substrate. A shallow, less defined print suggests the ground was firmer and drier. Sometimes you can even see slip marks, where a dinosaur's foot slid in the slick mud as it struggled for purchase. A tiny fossilized moment of clumsiness from a 70-ton animal. By reading this story in the rocks, the ichnologist becomes a set designer, reconstructing the ancient stage upon which these creatures lived their lives. We now have our character, we have its motion, and we have the detailed setting. All the pieces are in place for the final and most exciting step in the process: reconstructing the plot of the story. This is where ichnology transitions from the study of individuals to the study of populations, and where the most profound secrets are revealed. The real power of the Patagonian track sites lies in the fact that they often preserve not just a single trackway, but dozens, sometimes hundreds, of trackways all on the same surface. By looking at the relationships between these multiple trackways, scientists can begin to reconstruct the social behavior of these long-extinct animals. This is where we move beyond simple locomotion and start to see the evidence of complex living societies. The most important question that multiple trackways can answer is that of herding. If you find a large number of trackways from the same type of dinosaur, all on the same rock layer, all heading in the same general direction, and all moving at a similar speed, you have powerful, undeniable evidence for herding behavior. This is not a random collection of individuals wandering around. This is a coordinated group, a herd moving together as a single social unit. This kind of evidence is a paleontological goldmine. An animal's skeleton can never tell you if it lived in a herd, but its footprints can. By analyzing the patterns within these mass track sites, we can learn even more. We can look at the spacing between the different trackways to get a sense of how closely packed the herd was. We can look at the distribution of different sized footprints to understand the age structure of the herd. Did it consist only of large adults, or was it a mixed group of adults, subadults, and juveniles? This allows us to infer things about their family structures and their reproductive strategies. The direction of the trackways can also tell a story. If you have multiple large track sites in a region, and they all show herds moving in the same general direction, it can be strong evidence for seasonal migration. We can begin to map the great migratory routes of these giant animals as they moved across the landscape in search of food and water, much like the great wildebeest migrations in Africa today. And, in the most exciting and rare of cases, we can find the trackways of different kinds of dinosaurs interacting. Finding the tracks of a large theropod predator overlapping or moving parallel to the tracks of a herd of herbivores is a tantalizing clue. While it is incredibly difficult to prove that the tracks were made at the exact same time, it provides a frozen moment, a snapshot of a potential predator-prey interaction. It is the closest we can ever get to watching a prehistoric hunt unfold. We can see the predator shadowing the herd, perhaps looking for a weak or young individual to attack. This is the ultimate goal of the ichnologist, to reconstruct not just the animal, not just its movement, but its behavior, its social life, and its interactions with other creatures. The footprint becomes a window into the mind of the dinosaur. By carefully reading the tracks, by following this step-by-step process of scientific deduction, we can transform a simple set of depressions in the rock into a rich and detailed story. A story of life, movement, and drama from a world that has been lost for 100 million years. And the stories being revealed in the great track sites of Patagonia are some of the most spectacular of all. We have learned the language of the tracks. We have seen how the science of ichnology allows paleontologists to transform a simple fossilized footprint from a static depression in the rock into a dynamic record of a living, moving animal. We can now identify the track maker, calculate its size and speed, and reconstruct the ancient environment it walked through. Now, armed with this knowledge, we can return to the vast, windswept plains of Patagonia and begin to read the incredible stories that have been written in stone. The track sites discovered here are not just isolated footprints. They are entire pages, sometimes entire chapters, from the lost book of the dinosaurs' lives. They reveal secrets of social behavior, family structures, and predator-prey interactions that bones alone could never tell us. This is where the science becomes a story, a series of astonishing revelations that bring the world of the Patagonian giants to life. The first, and perhaps most profound, of these stories is the one told by the thundering footsteps of the herding titans. For many years, the giant sauropod dinosaurs, the titanosaurs of Patagonia, were often depicted as solitary, slow-moving creatures. Because of their immense size, it was thought that they might have been too large and consumed too much food to live together in large groups. The popular image was of a lone giant, lumbering through the landscape, a majestic but isolated animal. The fossil trackways of Patagonia have completely shattered this image. At numerous sites, most famously at the Lake Ezequiel Ramos Mejia site in Argentina's Neuquén province, paleontologists have discovered vast surfaces of rock, ancient mudflats that are literally covered in the fossilized footprints of sauropods. And these are not just a random jumble of tracks. What makes these sites so extraordinary is that they show dozens of parallel trackways, all from the same type of sauropod, all moving in the same direction, and all moving at a similar steady walking pace. This is the smoking gun for herding behavior. This is not a coincidence. This is the fossilized record of a massive herd of giant dinosaurs on the move. The implications of this discovery are immense. It fundamentally changes our understanding of sauropod biology and behavior. It tells us that these colossal animals were not solitary loners. They were highly social creatures. They lived, ate, and traveled together in large coordinated groups. But why would they do this? The most likely reason is the same reason that modern-day elephants or wildebeest form herds: safety in numbers. Patagonia, as we know, was home to some of the largest and most terrifying predators that ever lived, giant carcharodontosaurids like Giganotosaurus and Mapusaurus. A single, isolated sauropod, even a large one, would have been a tempting target for a pack of these killers. But a massive organized herd would have been a much more formidable and dangerous proposition for any predator. The sheer size of the herd, the thundering sound of their footsteps, the chaos of their massive legs and tailsit would have been an intimidating and confusing wall of flesh. A predator would have had a much harder time singling out and attacking an individual within the safety of the group. The herd was a moving fortress, a collective defense against the giant carnivores that stalked their world. The herding behavior also suggests the possibility of long-distance migration. A vast herd of 70-ton animals would have consumed an incredible amount of vegetation. They would have had to be constantly on the move, like a slow-moving storm of consumption, traveling across the landscape in search of fresh feeding grounds. The trackways, which often show a consistent direction of travel over large areas, may be a record of these great seasonal migrations. We can imagine these herds moving across the Patagonian plains, following the rains and the seasons, their lives dictated by an ancient rhythm of movement that was passed down through generations. This discovery transforms our image of the sauropod. It is no longer just a big, dumb eating machine. It is a complex social animal, capable of coordinated group behavior and long-distance navigation. The footprints give us a glimpse into the sophisticated social lives of these giants, revealing a level of complexity we never before thought possible. And as scientists looked closer at the structure of these fossilized herds, they discovered another, even more touching and profound secret. The discovery of herding behavior was a major breakthrough. But some of the Patagonian track sites revealed a level of social complexity that was even more surprising, a pattern that seems to speak of family, care, and the protection of the young. At some of the sauropod track sites, paleontologists noticed a fascinating and recurring spatial arrangement of the footprints. The trackways were not randomly distributed. Instead, there was a clear pattern. The largest footprints, belonging to the giant, fully grown adults, were consistently found on the outside edges of the herd. In the center of the group, protected on all sides, were the much smaller footprints of the juvenile and subadult sauropods. This is an incredible discovery. It is the fossilized evidence of a sophisticated and deliberate social strategy. The adults were actively protecting their young by forming a living, moving barrier around them. They were putting their own massive bodies between their vulnerable offspring and any potential threat from the giant predators that roamed the landscape. This is a behavior we see in many modern social animals, most famously in elephants. An elephant herd will often travel with the calves in the center, surrounded by the protective circle of the large adult females. It is a powerful and effective way to ensure the survival of the next generation. To find the exact same pattern preserved in the 100-million-year-old footprints of dinosaurs is simply astonishing. It suggests a level of parental care and social cohesion that goes far beyond simple herding. This wasn't just a loose aggregation of individuals. This was a true family group, a clan, with a complex social structure and a deep, instinctual drive to protect its young. It paints a picture of the giant sauropod adults as more than just mindless eating machines. They were watchful parents, attentive guardians who understood the dangers of their world and took active steps to mitigate them. We can almost imagine the scene: a young, inexperienced sauropod wandering too close to the edge of the herd, only to be gently nudged back towards the center by the massive leg of its mother or another adult female. This discovery gives us a rare and beautiful glimpse into the tender side of these giants. It shows us that the lives of the dinosaurs were not just about a brutal, constant struggle for survival. They were also about family, about community, and about care. The footprints allow us to see an intimate moment in the life of a dinosaur family, a moment that was frozen in the mud and preserved for 100 million years. The evidence for this protective herding behavior is one of the most powerful and moving stories ever revealed by the fossil record. It connects us to these ancient creatures on a deep, emotional level. The story of the herbivores is one of social cooperation and defense. But what about the predators? What do the footprints tell us about the lives of the terrifying carnivores that hunted these herds? The footprints of the giant theropod predators of Patagonia, the carcharodontosaurids like Giganotosaurus and Mapusaurus, tell a more complex and sometimes contradictory story. For many years, the prevailing image of these giant carnivores, much like T-Rex, was that of a solitary hunter, a lone king of its territory. And many of the theropod trackways found in Patagonia seem to support this view. Scientists have found numerous long, single trackways of a large theropod, a lone individual walking across the landscape, clearly on its own. This suggests that solitary hunting was, at the very least, a common strategy. We can picture a single Giganotosaurus, a 40-foot-long predator, stalking the edges of the great sauropod herds, using its keen senses to look for any sign of weakness in old, sick, or young animal that had become separated from the protection of the group. This image of the lone superpredator is powerful and deeply ingrained in our imagination. But other discoveries have presented a different, and even more terrifying possibility. At the same site where the bones of multiple Mapusaurus individuals were found together, paleontologists also found a track site that seemed to confirm the most exciting theory about this predator, that it may have hunted in packs. The track site revealed multiple parallel trackways of large theropods, all moving together in the same direction, at the same time. This is the same kind of evidence that is used to prove herding in herbivores. But in this case, it suggests a coordinated group of giant killers on the move. A pack. The idea of a pack of 40-foot-long predators, each armed with a skull full of steak knife teeth, is the stuff of nightmares. But it makes a great deal of ecological sense. While a single Mapusaurus might have been able to take down a juvenile sauropod, tackling a half-grown, multi-ton subadult would have been an incredibly dangerous proposition. The sauropod's massive tail could have been used as a devastating whip, and its sheer body mass could have crushed a predator that got too close. But a coordinated attack by a pack of 6 or 7 giant theropods would have changed the odds completely. They could have worked together to harass the herd, to separate a target from the group, and to attack it from multiple angles at once. Their collective power would have been enough to bring down much larger and more dangerous prey than any single individual could have hoped to kill. This evidence for pack hunting behavior in some of the largest carnivores ever to live is revolutionary. It suggests a level of social intelligence and cooperation in these giant predators that we are only just beginning to appreciate. They may have had complex social structures, with hierarchies and coordinated hunting strategies, much like a modern wolf pack. Of course, the debate is not completely settled. Some scientists argue that these multiple trackways might just represent a group of individuals that were drawn to the same place at the same time, perhaps a waterhole or a large carcass, but were not necessarily a cohesive social pack. But the evidence for cooperative hunting is growing, and it is changing our view of these creatures from simple killing machines into sophisticated and intelligent social predators. And in a few exceptionally rare cases, the tracks of the hunter and the hunted are found together, giving us a tantalizing glimpse of the prehistoric drama as it unfolded. This is the holy grail for an ichnologist, to find the fossilized evidence of a direct interaction between a predator and its prey. These discoveries are incredibly rare, as they require a very specific and unlikely set of circumstances to be preserved. You need both the predator and the prey to walk across the same soft patch of mud, at more or less the same time, and for their tracks to be preserved together before they can be erased. But in a few remarkable locations in Patagonia and elsewhere in the world, just such a scenario has been found. These sites appear to preserve a frozen moment from a prehistoric chase scene. At one famous site, you can see the trackway of a medium-sized herbivorous dinosaur walking at a normal pace. A little further along, the trackway of a large theropod predator appears, intersecting the herbivore's path. And at the point where the two paths meet, the herbivore's tracks suddenly change. The stride length increases dramatically, the prints become deeper, and you can see signs of slipping and sliding. The animal has broken into a desperate, panicked run. The predator's tracks also change, its stride lengthening as it gives chase. It is impossible to know the final outcome of this particular chase. The tracks run for a short distance and then disappear, as the animals moved onto harder ground that did not record their prints. Did the herbivore escape? Or did the predator make its kill just a few yards beyond where the tracks end? We will likely never know for sure. But the tracks themselves are a breathtaking piece of storytelling. They are a fossilized narrative of fear, speed, and the brutal reality of the struggle for survival in the Cretaceous world. These chase sequences are the most dynamic and exciting stories that footprints can tell. They allow us to witness a moment of pure, high-stakes drama from 100 million years ago. While a definitive hunt scene with clear evidence of a final struggle and a kill has yet to be found in Patagonia, the potential is there. Each new track site that is discovered holds the possibility of revealing just such an incredible tableau. The stories written in the stones of Patagonia are a powerful reminder that the fossil record is not just about death and anatomy. It is about life and behavior. The footprints of the herding sauropods, the protective families, the lone hunters, and the potential predator packs all combine to create a rich and detailed picture of a lost world in motion. They are the ghostly echoes of the giant's footsteps, a story that connects us, across the gulf of millions of years, to the real living creatures that once ruled this incredible land. The stories written in the stone of Patagonia are breathtaking. Through the science of ichnology, we have followed the footsteps of giants, uncovering remarkable evidence for herding titans, protective families, and terrifying packs of predators. These individual stories are fascinating, but when we step back and look at the bigger picture, we realize that these footprints are doing more than just telling us about the behavior of a few dinosaurs. They are fundamentally reshaping our entire understanding of the world these creatures inhabited. The tracks are a key that unlocks some of the longest-running and most important debates in paleontology. They are providing new and powerful answers to fundamental questions about dinosaur biology, their environment, and their very nature. We will now explore these broader implications, to see how these ghostly echoes from the past are helping to build a more complete, dynamic, and surprising picture of the entire dinosaur ecosystem. The first major debate that the footprints are helping to solve is the question that has been at the heart of dinosaur science for decades. For most of the 20th century, dinosaurs were envisioned as giant, slow, and stupid reptiles. They were seen as being cold-blooded, or ectothermic, just like modern lizards and crocodiles. This meant that, like their modern relatives, they would have been dependent on the external environment for their body heat. This cold-blooded model implied that they would have been sluggish, slow-moving animals with a slow metabolism, needing to bask in the sun to warm up and become active. This image of the lumbering, slow-witted dinosaur dominated our popular culture. But in the 1970s, a dinosaur renaissance began, led by paleontologists who started to question this old orthodoxy. They pointed to the upright, athletic posture of many dinosaurs, the microscopic structure of their bones which showed fast growth rates, and the predator-prey ratios in fossil ecosystems, all of which seemed more consistent with a warm-blooded, or endothermic lifestyle, like that of modern birds and mammals. This sparked one of the biggest and most passionate debates in the history of paleontology. Were dinosaurs cold-blooded slouches or warm-blooded dynamos? The fossil trackways from Patagonia and other sites around the world have provided some of the most powerful evidence to help settle this debate. The tracks give us a direct record of the dinosaurs' activity levels and movement patterns. And what they show is a world of active, dynamic creatures, not slow-moving reptiles. The evidence for sustained, long-distance herding and migration in the giant sauropods is a powerful argument against a simple cold-blooded metabolism. A 70-ton cold-blooded animal would have immense thermal inertia. It would take a very long time to warm up, and a very long time to cool down. But it is difficult to imagine how such a creature could sustain the high, consistent energy levels needed for walking hundreds of miles in a coordinated herd. The tracks show these animals engaged in continuous, purposeful movement, a lifestyle that seems to require a much higher metabolic rate, something more akin to a warm-blooded animal. The speeds calculated from the trackways also support this. While the sauropods were not fast runners, their steady walking pace was consistent and efficient. And the theropod predators were clearly capable of brisk trots and, in some cases, fast runs. This level of athleticism is hard to reconcile with a slow reptilian metabolism. The current scientific consensus is that the reality was likely somewhere in the middle. Most dinosaurs were probably not fully cold-blooded or fully warm-blooded in the modern sense. They likely possessed a unique intermediate metabolism, a state known as mesothermy. They could generate some of their own body heat, giving them a higher activity level and endurance than a modern reptile, but perhaps not as high as a modern mammal. The giant sauropods also benefited from gigantothermy. Their immense body size meant that they would have lost heat very slowly, allowing them to maintain a high and stable core body temperature. The footprints are a crucial piece of this puzzle. They provide the behavioral evidence that complements the anatomical evidence from the bones. They show us unequivocally that the dinosaurs were not the sluggish, lumbering failures they were once thought to be. They were active, energetic, and highly successful animals, and their warm-bloodedness was a key part of that success. The tracks give us a glimpse into the true energetic engine of the dinosaur world. And they also give us a much clearer picture of the stage upon which this energetic world played out. The fossil footprints do more than just tell us about the animals themselves. They provide an unparalleled insight into the specific environments the dinosaurs inhabited. A skeleton found in a rock layer tells you that the animal died near that environment. But a footprint tells you that the animal was actively living and moving within that environment. The tracks allow us to map the dinosaurs' habitats with incredible precision. By studying the distribution of different types of tracks in different types of sedimentary rock, we can build a detailed ecological map of the past. The Patagonian tracks sites, for example, show us that the giant titanosaur herds spent a great deal of their time on vast semi-arid floodplains. Their tracks are most often found in the layers of ancient mudstone that were deposited by the slow-moving, braided river systems that crisscross these plains. This was their prime habitat. We can picture them moving along these river corridors, using them as migratory highways and sources of water and food. In contrast, the tracks of some of the smaller herbivorous dinosaurs are often found in different settings, perhaps in the more densely vegetated areas away from the main river channels. The tracks of the theropod predators are often found shadowing these herbivore track sites, showing that the hunters were going where the food was. This level of detail allows us to move beyond simply saying dinosaurs lived in Patagonia, and to start making much more specific statements, like herds of Patagotitan migrated along the western floodplain of the New Cane River system, while packs of Mapusaurus likely ambushed them from the slightly more vegetated areas along the banks. The tracks also reveal the dinosaurs' preferences and behaviors within these environments. We can see where they walked and, just as importantly, where they didn't. For example, if we see a large track site where all the trackways seem to go around a certain area, it might indicate that the dinosaurs were avoiding a patch of unstable, deep mud or a dense thicket of unfamiliar plants. We can see them walking along the edges of ancient lakes, leaving behind a record of the prehistoric shoreline. This intimate connection between the animal and its environment is something that bones alone can rarely provide. It allows us to reconstruct the entire ecosystem in motion. We can see how the different species were partitioned across the landscape, how they used the resources available to them, and how they navigated the challenges of their world. The footprints transform our understanding from a simple list of species into a living, functioning ecosystem. They provide the ecological context that gives the story of the bones its true meaning. They are a bridge between the animal and its world, allowing us to see not just the creatures, but the very landscape they saw, the very ground they felt beneath their colossal feet. And this more intimate, dynamic view of the dinosaur world inevitably changes our entire perception of who these animals were. Perhaps the most profound implication of the Patagonian footprint discoveries is how they have completely transformed our vision of the dinosaurs themselves. The evidence for complex social behavior, herding, family structures, parental care, and pack hunting forces us to discard the old image of the dinosaur as a simple, solitary, mindless monster. These were not just giant lizards. They were complex and sophisticated social animals, with behaviors that were likely as complex in their own way as those of modern elephants or wolves. The evidence for herding in the giant sauropods is particularly revolutionary. The level of coordination required to move a massive herd of 70-ton animals across a landscape is immense. It implies that these creatures had some form of communication to keep the herd together and moving in the right direction. It might have been low-frequency vocalizations, too low for the human ear to hear, that could travel over long distances. Or it could have been visual signals like the posture of the head or the movement of the tail. Whatever the method, the coordinated trackways are proof that this communication was happening. The evidence for protective family structures, with the adults shielding the young, is even more significant. It suggests a level of social intelligence and instinctual care that we once thought was reserved only for mammals and birds. It shows us that the bond between a mother and her offspring, one of the most powerful forces in the natural world, was likely just as strong in these giant dinosaurs 100 million years ago. This changes our emotional connection to these animals. It is one thing to marvel at the size of a giant skeleton. It is another thing entirely to see the fossilized evidence of a mother protecting her child. It makes these creatures feel more real, more relatable, and far more intelligent than we ever gave them credit for. The same is true for the evidence of pack hunting in the giant theropods. A pack hunter is not just a mindless killing machine. It is a cooperative social animal. It requires communication, strategy, and a social hierarchy to be successful. The possibility that creatures like Mapusaurus were engaged in such complex behaviors elevates them from simple monsters to intelligent and formidable social predators. All of this evidence, taken together, is closing the perceived gap between the dinosaurs and the advanced animals of today, like birds and mammals. We are now beginning to see the dinosaurs as they likely were. A diverse and highly successful group of animals with a rich and complex behavioral repertoire. They had families, they had societies, they had strategies. The footprints have given us a window into their souls, revealing a depth and a complexity that we had previously thought impossible. They were not failures destined for extinction. They were the masters of their world for an unimaginable length of time, and their success was built on the foundation of their sophisticated social lives. And yet, for all that the footprints have taught us, they have also opened up a whole new world of questions. Every great discovery in science answers some questions, but it always raises even more new ones. And the trackways of Patagonia are no exception. While they have revealed so much about the secret lives of the dinosaurs, they have also highlighted how much we still don't know. The evidence for herding is strong, but it leads to a host of new questions. Did these herds have a fixed social structure? Was there a dominant matriarch or patriarch who led the group, like in an elephant herd? How did they make collective decisions about where to go and when to move? The tracks show us that they moved together, but the complex social dynamics that govern that movement are still a complete mystery. The evidence for pack hunting and theropods is equally tantalizing and equally mysterious. If they hunted in packs, how did they coordinate their attacks? Did they have specific roles within the pack, with some individuals driving the prey and others making the kill? How did they share the spoils of a successful hunt? The footprints show us that multiple predators were moving together, but the intricate details of their cooperative strategy remain hidden from us. And what about communication? The complex social behaviors we are seeing in the tracks must have been supported by some form of communication. We know from the structure of their skulls that many dinosaurs had excellent hearing and sight. But what did they sound like? Did the titanosaurs communicate with deep, rumbling calls that could travel for miles? Did the theropods use a combination of calls and visual displays to coordinate their hunts? These are questions that footprints alone cannot answer. But they are the exciting new frontiers of research that the footprint discoveries have opened up. Each new track site that is discovered in the vast, unexplored territory of Patagonia is a new opportunity to find more clues. Perhaps one day we will find a track site that preserves a more detailed interaction, a more complex social grouping, or a more complete predator-prey scenario. The story is still being written, or rather, it is still being uncovered. The footprints are a reminder that the world of the dinosaurs is still full of secrets, and that there is always more to learn. They are an invitation to keep searching, to keep digging, and to keep following the footsteps of the giants. The dinosaur footprints of Patagonia are a direct connection to the deep past, a ghostly echo of a lost world. They allow us to walk alongside the giants, to trace their journeys, and to glimpse their secret social lives. More than just bones, these tracks are stories written in stone, forever changing our vision of these magnificent creatures. If the past still whispers to you, don't forget to like, share, and subscribe. Ancient Relics Keeper, because some mysteries were never meant to be buried.